We actually have at NAU, we have a really strong connection with Sandia because two of the I don't know, they were sort of like upper echelon researchers ended up coming and working in our department. So we have a pretty strong sort of bridge between these two. They also have a center there. It's called the Center for Integrated Nanotechnology, or CINT. So we send people over there because they have really great equipment. But it's nice having that as a collaboration.
So
About
then you
4 hour
can
drive
talk
from
to
here. So.
yeah, you can talk to Whitney and also Steve. Yeah.
Yeah. Okay. So are they still at the postdoc level, or are they beyond that?
Yeah, all staff member over there.
Staff member. Okay, cool.
Yeah,
That's
they
great.
already.
Oh.
Whitney was promoted very fast, Okay. She
Yeah.
has a lot of advantage. So
Yeah, I know. Yeah, for sure.
yeah.
Have you spoken with Wilson in a while?
Well, so I spoke to him last year. Originally, he's supposedly to give a talk last year, but he has some other issues. I guess he actually finally gave up. Recently, I did not contact him.
Yeah.
You talked to him yet recently?
Yeah, I talked to him on occasion, but he's I guess he's had a pretty tough time with the pandemic because he's got 3 kids at home and is trying to, educate them and so forth while still working at the same time. So
Yeah, he has a very big labs over there.
yeah, I know. I
Two
know.
labs, actually.
Yeah, exactly. Yeah. I still haven't gone up to visit him yet. I'm not really that far away, but yeah, I just haven't had time to go see him. But I guess nobody really goes anywhere right now, though.
That's right.
Yeah.
That's good.
So I ended up getting tenure, so that was a nice relief.
Yeah, I guess you already become associate professor, right?
Yeah, yeah. So that became official last year. So that's a nice you know, I can relax a little bit now.
I thought that you always be relaxed.
Well, that's how I might seem, but
You're not thinking about to move to another location?
yeah, it's crossed my mind. I do like it here a lot, though. It's a nice place to live, and
I
the
know it's a
department's
nice
growing.
place. It's really a nice place, but there's so many other nice places as well.
Yeah, it's true. Like Athens, you mean?
No, not Athens. For example, like Hawaii, right? Hawaii is
Hawaii,
also a
yeah,
nice
yeah,
place, right?
that'd be nice. I'd go to Hawaii. Yeah, I would.
San Diego, right? It's also a nice place.
Yeah, yeah. I like skiing a lot now, though, so I have to go somewhere where I can ski.
Okay.
Yeah,
Yeah. So I think it's going to be my 9. So I welcome all of you, and then I'll ask Shashank to start maybe. Yeah. Can show the
Actually, a very
program.
good morning to all of you, and welcome to the second day of the International Conference on Sculptured Thin Films, GLAD 2021. So we are going to start the session. We have with us the session's chairperson, Professor Rupali Nagar today. And Dr. Rupali Nagar is an associate professor at Symbiosis Institute of Technology, Pune. She received a PhD degree from IIT Delhi and has been associated with IIT Kanpur and IIT Madras. She is actively working on the development of nanomaterials for gas sensors at room temperature and engineering physical properties of nanomaterials to enhance their catalytic properties. Now, I would like to request Professor Rupali Nagar to chair this session. Over to you, Professor Rupali.
Thank you, Shashank. Hello, everyone.
Yes, please proceed.
do you want me to start now, or?
Yeah.
Yes, please. Dr. Rupali, you can introduce the speaker of the day today.
Dr. Shashank, am I audible?
Yes, yes, you're audible. Yes.
Yeah, maybe perhaps in between it got muted, but anyway,
Okay.
yeah. So I was saying good evening, Professor Gibbs, and morning and good day to others in the session who have joined from different parts of the world. And we have very interesting talks lined up in this session. And first of all, I would like to thank Professor JP Singh and the organizers to have me as e-chairperson for this conference on GLAD. And let's begin with the first session. So welcome, Professor Gibbs. And, Professor Gibbs is an associate professor in the Department of Applied Physics and Material Science at North Arizona University. He's also a core faculty for the Center of Materials Interfaces in Research and Applications at Arizona University. Prior to this, he was at Germany, where he did his postdoctoral fellowship at Max Planck Institute for Intelligent Systems in Stuttgart. His present areas are the fabrication and optical properties of metamaterials with nanoscale features, and active transport and collective behavior of self-propelled particles at the micro and nanoscale. So over to you, Professor Gibbs. Let's hear you out.
Okay, thank you for the introduction, and thank you, JP, for organizing the conference and for inviting me. So I need to share my screen, I believe. So let's see if I can get this to work. Does this seem to be working okay?
Yes, we can see it. Yeah.
Okay.
It's visible.
Great. Okay. Okay. Yeah, so thanks again. Yeah, so I've been working with glancing angle deposition for quite a long time. So my PhD advisor, Yiping Zhao, is actually here in the audience, and this is where I first learned the technique. And then later on, Pierre Fischer, he was my postdoc advisor in Germany, and we sort of took that idea of GLAD and tried to squeeze it down to the nanoscale a little bit more. So it's something I've been working on for a while. In my current lab right now, we have a few different projects that are all associated or basically revolve more or less around glancing angle deposition. So the two main areas of focus are going to be the self-propulsion of active particles, which I think that you've maybe heard a little bit about a little bit yesterday, and the other one being the optical properties. So we've, in particular, been looking at the chiral structures and their interaction with circularly polarized states of light. So today what I want to do is I want to talk about a very specific project, which is looking at active particles that are light activated. So in particular, what we use in my lab is titanium dioxide, which is going to interact with ultraviolet light, and through a catalysis reaction, we are going to be able to get these particles to propel themselves. And the nice thing about this type of process is that we can actually turn their activity on and off, and we can also control how strong the self-propulsion is exhibited by the particles themselves. So let's get into it. So this first slide I'm going to show you here, this is actually, it's a very simple experiment. What we've done is we've taken water and hydrogen peroxide and thrown some titanium dioxide nanoparticles into the solution. And so what you're seeing here is that the particles are going to come together, but when we turn the ultraviolet light on, they start to move apart. So you see some of this sort of collective, interesting looking collective behavior. However, you might recognize that the patterns that are being formed are fairly random. And what we want to do is see if we're able to utilize glancing angle deposition in order to get this type of movement, this type of behavior to be a little bit more controlled than what we see here. Okay, so the first thing that we wanted to look at, and I just want to mention that this was actually done by Pierre Fisher's group beforehand, so they were to this idea before we were, but this interesting idea of taking TiO2 and putting it onto an SiO2 underlayer. And so if you look at the top left, that's an SEM image that shows TiO2 that's been distributed on half of a spherical particle of silicon dioxide. And what we end up getting here is, because of the difference in the two different phases, we have one active side and one inert phase. Then there's this complicated chemical reaction and phoretic behavior that ends up leading to the self-propulsion of the particles. So one of the nice things about this project is that there is, as you probably know, there's a huge amount of research that's being done on a regular basis for photocatalytic materials, right, for converting sunlight into energy and so forth. And so we've taken some of those ideas and we've determined that we can actually utilize some of the same processes in order to gain better control over the way these particles are going to not only self-propel, but also interact and self-assemble with each other. So this is a really simple process to fabricate this particular, which is the Janosphere. So the way we do this is that we take the silicon dioxide particles and we functionalize them so that they become hydrophobic. So they'll actually sit right on top of a water. And so we have a bath of water, and they will, the lowest energy configuration is going to lead to these being in a close packed monolayer of spheres. And they'll float right in the water, and then we can actually use these barriers to push inward as the substrate's pulling out. So the barriers are important because if you don't have the barriers pushing inward, then what you find is that you'll end up getting gaps, and you won't really get this nice continuous monolayer over the entire film. So that's a nice process that will give you, it's not exactly single crystalline, right, but it is a monolayer, but you do have some defects in the crystal there. But however, we want to take advantage of GLAD, and with GLAD, you really want to have a patterning across the entire substrate. Yeah, so the next step would be to just deposit titanium dioxide directly on top of the spheres. And then we have this annealing process just to get them into the correct crystal phase, the anatase crystal phase. We use ultrasonicator to remove them from the surface. And once they're in a solution of hydrogen peroxide, then we can use the fluorescence microscope, right? The activating light, the ultraviolet light from a fluorescence microscope, in order to get these things to start moving around. So later on in the talk, I'll show you some different tricks that we play in order to get the particles to move without any hydrogen peroxide, right? They can actually just move in water alone, but we're going to have to change around the materials properties a little bit, and that's one of the main areas of research for this particular project here. Okay, so here is what these particles look like when they are activated. So if you take a look at the video down here in the bottom left, there's sort of an interesting phenomenon occurs. If you look at that sort of black spot there, that is, I'm not entirely sure what that is, but I believe it's a piece of the silicon substrate. And what you'll notice is that when the light is turned off at the beginning of the video, the particles do have a little bit of motion. They have Brownian motion. That's just thermal fluctuations of the fluid itself. But when we turn the light on, the particles, they start to self-assemble, and they can actually grab on to that piece of cargo and move it around. So I don't want to give you the impression that this is a very controlled process, but it gives you an idea of potential applications that we could imagine in the future when we have, if we have the desire to pick up a piece of cargo, take it somewhere else, and then drop it off. This could be a feasible way of doing that. Okay, so as the video starts, again, that's Brownian motion, and now UV light turns on. You start to see this self-assembling process, and the particle is being picked up, this other particle in the solution. Turn the light off and then back on again, so we can translate this back and forth between self-assembly and the Brownian motion that's going to cause these cause them to release the cargo. You also see that you have these crystal formations, which has been studied in detail by other groups. But again, this is a fairly straightforward process to get this to work. If you look closely at the video, you can actually see in the images in the top right too, you can actually kind of see where the titanium dioxide is. It has a high index of refraction, so it looks darker than the rest of the spheres. And that way you can really tell, which direction they are moving. So something that's a little bit interesting about these is that they seem to rotate a little bit downward and sort of slide across the surface, slide across the interface, which I think I'll talk about a little bit more later on in this talk. Yeah, okay, so getting into glancing angle deposition. So let's just take the same exact idea that we had for the Janosphere and just make new Janospheres that have slightly different morphology to them. So you can imagine using glancing angle deposition, we can, instead of depositing the TiO2 directly on top of the spheres, we're going to tilt the substrate, right, to about 85 degrees and deposit a very thick layer of titanium dioxide, thick enough to the point where it's kind of pushing the limits of the system. So I think we're depositing something like 6 or 7 microns of TiO2. But overall, it's really the same exact process as designing the spherical Janus particles as well. So tilt it to an angle, deposit quite a bit of TiO2, do the annealing process again, put them into water and H2O, or H2O2, sorry. And then we are going to look at their behavior. And so what's kind of interesting about this is that we start to find out that the morphology, not just the material properties, right, the catalytic parts of the structures, but also the morphology, right, the shape of the particles is going to have a large influence on the way that they move and self-assemble. So you see in the top, there's some SEM images of the final product on the substrate. So you can see the nice monolayer film. And then as we deposit the TiO2 at an angle, it grows these columns that are kind of tilted a little bit. Okay, so let's take a look at the video down in the bottom right and see them in action. So here we go. So UV is off at the beginning, and then they turn on. And so one thing you might notice, there's a lot going on here, right? There's a lot of particles, but we also, we see the same type of behavior where the particles self-assemble, just like we did for the Janospheres. However, you might notice that there are some other types of motion in there as well. So they don't really all behave the same way. Some of them move translationally, some of them move in a rotational fashion. And so what we wanted to do is to try to figure out, what is special about the morphology that leads to these types of motions so that we can predict it in the future, right? So if we want to have specific type of movements, then we can hopefully engineer this directly. So that was part of our goal. So the first thing we did is I had sort of like a plethora of undergraduate students who worked on this project, but what I wanted to do is just get some statistical data about how the particles interacted with each other, or actually before that, we looked at the way that the individual particles move by themselves. One of the current projects we're working on now is looking at these high density situations. So these particles, again, they're spheres with this elongated TiO2 tail. And you can see some of these sort of interesting patterns starting to form when the light is turned on and off. So at the beginning of this video here, the light is off, now it's on. You can see them starting to self-assemble. It's not the clearest video, but you can get sort of an idea of what's happening here. So once the light is off, they relax back into basically a nice monolayer on the surface. But when the light is on, you get these patterns starting to form. Okay, so I had these. Let me go back to that in just a minute. I had a bunch of undergraduate students who worked really hard on this project, and what the idea was is that they wanted to take a look at just a very simple parameter to find out how that's going to affect the movement. And what they did is they just changed the length, right? So nothing too difficult to do. Just when you have that angle deposition, instead of doing a small amount, you do a longer amount, and then you look at what happens in between too. So one of the things that was interesting, and it's still not entirely clear why this occurs, but we have some ideas, but it turns out that you actually get this threshold value where the particle will actually start to move in one direction, and And once the length of the tail gets a little bit longer, it'll actually switch directions. And we believe this has to do with the phoretic interaction between the fluid and the two different materials. And that interaction changes as a function of the geometry of the structures themselves. So this was a paper that came out 3 years ago or so in ACS, Applied Materials and Interfaces. If you want to take a look at some more details of that, and we have some more explanation of what we actually think is going on. This former slide here is actually just a video that gives you a little bit of an idea. If you take a close look at the particles, this was under a sort of fancy confocal microscope where you can get really good resolution. But one thing you might notice with these is that you can really kind of see the structure. And I think that everybody who messes with GLAD is probably aware of the fact that you don't always get the exact same, you don't have perfect repetition of the structure across the entire substrate. You get these small variations and so forth. And you can kind of see that in some of these particles. You also see that they can orient themselves differently, but there can be a little bit of variation. And that's what we expect to be the cause of the spreads and the different velocities that we're measuring here. So again, these plots are just saying, okay, I'm just going to change the length of the arm. How does the speed change, right? Just the magnitude of the velocity. But the plus, the positive and minus, right? That's going to be referring to which direction the particle is going, either towards the head or towards the tail. Okay. So we want to take this a step further, and really what the idea was for this project is we wanted to use multiple photocatalysts that have different band gaps, so energy band gaps. And what we were trying to go for is to be able to use two different colors of light, right? So we already know that TiO2 is going to be activated under ultraviolet light, but we looked for a bunch of different types of photocatalysts that are going to be active in the visible range too. So the one that we ended up falling on is copper oxide, so Cu2O. And we made them into these sort of jagged, sort of V-shaped structures in order to be able to analyze their movement better. So when we switch between the different fluorescent sources, hopefully we'll be able to know, if you look at the microscope image down here on the right side, you know that next to the sphere, that's the TiO2, and the one that is at almost what's a little bit less than 90 degrees, right? So it's probably like 75 degrees or so, is the copper oxide. So by using that morphology, we could at least sort of tune in or see what was happening when we had different light sources and how that corresponds to the material that they're made from. So yeah, from the standpoint of GLAD, it's the same exact process. We deposit TiO2 at an angle, and then we take our substrate and we just rotate it 180 degrees. And I imagine most of you are familiar with this already, but that's going to make this sort of V shape here. So the top piece being copper oxide and the bottom TiO2. Okay, so it didn't really turn out exactly the way that we wanted it to, because one of the problems is that, as you know, if your photon has a high enough energy to make the transition from the valence band to the conduction band, that's going to occur for a higher energy photon. So what I mean by that is that if you can excite this band gap transition in copper oxide, when you use ultraviolet light, you can make that transition in TiO2, but it's also going to be able to make a transition for the copper oxide. So that was sort of a bit of a bottleneck that we never really quite got around exactly. But one thing that we did discover, though, is that using different light sources, we're going to be able to have different types of movement depending upon the color of the light. Okay, so the idea here is that we have a heterojunction, right? So we have two different semiconductors and they're in contact with one another. I won't go into the details of the solid state physics here, but basically not only do we have two different photocatalysts that have different band gaps, but the intersection between the two materials is actually quite interesting too, because that changes the band structure where that heterojunction actually occurs. And so we're going to, a little bit later, I'll tell you a bit more about how we take advantage of those heterojunctions like that. So the image on the left side gives you an idea of what the structures look like again. So it sort of has this V shape, and the next slide is going to show some of their behavior. Okay, so the two different colors that we use, we had to use blue in order to make the transition from the valence to the conduction band for copper oxide. And so for blue light, we got this rotational type of movement. And you see for ultraviolet, that happened kind of quickly, but for UV, this was the primary type of movement that we saw, was this really rapid translational movement. And something that's kind of interesting about this too is that it seems, if you look at this figure on top here, the schematic C, it seems, it's hard to tell exactly by just looking at the microscope images, but it seems like the orientation with respect to the substrate actually changes too when the light turns on. So depending upon how that orientation changes will tell you whether or not you have translational rotation and motion. So I don't want to mislead you and tell you that we only got rotational motion with blue light and only translational with UV, because that's not exactly the case. And I think these the variations between the samples. So statistically, this is what happens, right? They're mostly rotational for blue, mostly translational for UV, but you do also see some rotational movement for ultraviolet. And I think this comes back to the fact that you're actually activating both of the semiconductors simultaneously when you have UV light present there. So anyway, it did work to some extent, but what we really wanted to do next, though, is to see if we could actually take advantage of those heterojunctions. So not just the fact that you have these two different band gaps for the two materials, but the interaction, the interface between the two can actually have a strong effect on their interaction with light. Okay, so that's what this study was about here. And so instead of using two different semiconductors, we actually just used gold. And so as you know, if we have an interaction, or we have an interface between the TiO2 and a metal like gold, it actually changes the band gap also. And what we wanted to do is to take advantage of GLAD in order to put the gold on different segments of the TiO2 tail. And so the two that we focused on was just putting it on the very end. So if you look at figure C here, what we did is we grew the tail just like the other slides I was showing you, and then we put the gold just directly on the end. So we kept the angle the same, and we just put the gold, we deposited gold at the same angle. Or what we did is for D, we took the substrate after the deposition of TiO2 and deposited it directly down, so it sort of coats the sides of these tails here. So we did indeed find different types of behaviors. So really the primary one is that when we only have TiO2 alone, so we've already seen these structures in action here, you see that they start to move towards the tail of the structure. So it's moving towards the TiO2, which you can tell by looking at the structure itself, because you have the sphere and the TiO2 is the darker segment. So what we found out, though, is that if you put gold on the very end, it will actually switch the orientation of the motion. And so what you find this other video here is that it actually switches directions. So just by adding that gold onto the end of the tail, it will change the behavior, right? Okay, so the one with the gold on the side was a little bit less interesting. We got some rotational motion primarily. I was expecting this to be a little bit more active because the interface between the two materials is larger for the one where you have gold on the side. However, it seemed to kind of make them stall out a little bit, which is not entirely clear why that occurred at this moment still. However, if we want to look at a little bit at the details of what's going on here, is that, again, we have this interface. When we have a photon, UV photon come in, we have this transition from, again, the valence band to the conduction band. But if we have this interface between the two materials, we actually get an electric field that builds up between them. And so what this does is the interface actually promotes the separation of the charges. So it enhances the photocatalytic activity. And depending upon which direction the charges are moving through the interface will actually dictate the direction that the fluid is going to respond to that movement of charges. So if the gold is located in different points of the structure, then you can actually get the fluid flow over the particle to go different directions. And so in that case, what you can do is you can tune the motion, hopefully. But again, so the one with the gold on the side, it didn't really work exactly the way that we wanted to, but it does at least with this primitive model that we've built here, it is consistent with the types of motion that we actually observe in the experiments. Okay, so this is, this is a project that's being currently worked on by one of my master's students. And so this is probably something that you're familiar with too. These are helical structures, so they're made out of TiO2. And he's actually looking at the behavior of helices when they're activated under UV light here too. So this is a video. It's not super clear, but at least you can kind of see, whoops. Hopefully you can kind of see what's going on. So it's a little bit hard to tell, but we're trying to determine whether or not these particles aren't just translating, but if they have some rotation translation coupling because of their sort of screw type shape, and whether or not that's coming from the phoretic behavior, or if it's just from the fact that they're moving translationally and the fluid's causing them to start to rotate. So that's what he's trying to figure out now, but that's been a pretty tricky thing to determine. But so we'll put that in the back burner for now, and just look out, maybe hopefully in a couple of years we'll have a paper about this one. But so my collaborator actually in Hawaii, Will Uspal, he came out with a theoretical paper recently that looks closer at this type of phenomenon if you're interested in looking at it. Okay, so I'm just about done, but I just wanted to let you know about one other paper that came out last year. So it was sort of a follow-up to the one where we had the gold TiO2 interfaces. And what we wanted to do is to see if, that first paper, we didn't actually look at how the amount of the metal actually affects the behavior. And so I had, this was again headed by an undergraduate student, but I had him just do different amounts of gold on this structure. If you look at the left side, so that's figure A, it's a tail of TiO2. It's kind of a little bit stubby, right? It's not a long tail like we had for the other ones. And then we just put gold directly on top of those tails. So this was done using glancing angle deposition. So we had, we tilted it to a large angle, and we spun the substrate rapidly during the deposition process. So you get these sort of like fat tails on the end of them like that. So a little bit different morphology than keeping the substrate at a fixed angle. So something that kind of was interesting about the results from this is that we found that there's actually an optimized amount of material that seems to enhance the catalytic behavior the most, which we found to be about 10 nanometers. And what we think is happening here is that once you deposit enough gold, what you really do is you end up completely covering up the surface. So you're basically no longer exposing as much TiO2 to the surface. And we think that that's where we find this sort of convergence to about 2 micrometers per second, is once we actually get a thickness that's thick enough that you actually have a more or less continuous film. However, we see for like a 10 nanometers from the literature, it's pretty well known that when you deposit using physical vapor deposition, that you're going to get these like islands, right? And so we think what's going on is that we have a much larger surface area. So you have these gold islands sort of decorating the tops of the TiO2. And in that case, what it does is it can really greatly enhance the catalytic behavior. So this was just a follow-up study on that. So yeah, I think that's all I want to say for now. And just wanted to let you know, the different people who are working on the project, and the financial support is coming from the National Science Foundation and the Research Corporation. And so thank you for your attention, and thanks for the invitation, JP. And yeah, I guess I can take some questions now if anybody has them.
Thank you, Professor Gibbs. A really interesting talk.
Thank you.
Yeah. Really nice to see how the different materials have been worked upon. So do we have some questions? The attendees may either raise hand or use the chat box.
I see Juan Ho here. Hey, Juan Ho. Haven't seen you in a long time. And Ambrish.
So are there any questions? Professor Gibbs, may I ask a question?
I think Professor Iping is asking some. So you may.
Okay, yeah. Yes,
Okay,
Professor.
maybe I'll first ask. John, in your beginning, when you try to do those self-assemble of those titanium dioxide coated particle, right? Have you ever tried to make those particles like an oval shape and then see how they can self-assemble?
Yeah, we have been looking. So you said an oval shape?
That's right, because if you put a little rod on top of it, it's really breaks the symmetry of the whole structure, you know.
Oh yeah, I see. No, we haven't tried that. We are looking currently at the self-assembly of the structures that I showed already, but I'm not really sure how you'd get the oval shape. Yeah, I'm blanking out because this is my PhD advisor, and I'm having flashbacks of my days in graduate school. But yeah,
That's fine.
yeah. So this is yeah. We're working on that at the moment, so it's kind of slowed down recently, but we have actually seen some really interesting stuff by changing the morphology and taking a look at how the self-assembly changes, and there seems to be some sort of critical threshold length that causes a different type of phase to emerge. That's sort of what I can tell you, at least qualitatively at the moment. But yeah, I think that there's lots of different types of morphologies we can try out with GLAD, hopefully.
Okay. Thank you.
Sure.
Any other questions do we have?
Yeah, I
Yes,
think,
Srikant can ask question now. Mr. Srikant.
Hello.
Yep. Go ahead.
Yes, Shrikant.
Hello, Professor Gibbs. It was a very nice talk.
Thank you.
So I have a question about that gold, TiO2 gold Janus particle. So as
Okay.
you know that, gold is a plasmonic particle. So does it play any role for the motion?
I believe so. Yeah, it's a great question. I actually meant to bring that up during the talk, but so one of the things that we found is when if you just have TiO2 by itself, we only are able to activate the particles when they're in H2O2. So we need to have hydrogen peroxide also. It turns out that when we add the gold segments on, we can actually drive these things in water alone. So I guess I imagine this is occurring due to water splitting. So it's basically a photochemical cell. But the fact that we also were getting this type of movement in water alone, with not just UV light, but we were seeing it with visible light also, and this was falling in the range that you would typically see this type of behavior from plasmonics. And so, yeah, I believe that is going to have some effect also. I just don't know specifically the details of it.
Okay, sir. And one more question is, what is the advantage of this head-tail type structure?
What is the advantage? Is that what you asked?
Yeah. Any specific advantage of this head-tail type structure?
Yeah, so what we really found is that, depending upon, using GLAD where we actually place the gold. And so, as you know, GLAD allows you to, gives you some pretty good control over this. You can actually change the behavior just by placing the gold in different locations. And the other thing too is that you can actually activate the particles in water alone, and you can look at these types of. So this is actually one of the problems in this field, right? Is that using hydrogen peroxide can be kind of a messy business. Sometimes you get these formation of oxygen bubbles that kind of disturb your fluid, and it makes things difficult to see what's happening. And also, it's a chemical that's toxic and so forth. But it's nice to be able to do these experiments in just water alone. So those are the primary, at least in my opinion. There might be some other ones too.
Okay, I think we can just allow one more question, keeping the time limit in mind. Professor Ambarish?
Yeah. Hi, John.
Hey,
Good
Ambrish.
evening. Hi, good evening. Very nice talk, very nice work.
Thanks.
Good to see you. John, I had a question about that movie that you had shown a little bit at the beginning of the talk. When you had this passive colloidal particle and all the active swimmers were sort of circling around it, right? Now, I wonder if you keep on trying to increase the activity, is there some sort of a limiting density that that one obtains as you try to increase it more and more?
So are you talking about the one where it was, the quote unquote cargo that was being picked up?
Yes. Yes.
Okay. Yeah, I'm not sure. That's actually a really interesting question, right? So if you look at the overall density, if we get the same type of behavior, which I believe is what you're asking, is that if you were to increase the particle density, do you get the same types of behavior? I imagine from what we've seen, at least qualitatively, if you have too high of a density, then you actually start the particles become kind of jammed into these crystals, and then they don't really move a whole lot. But it is sort of interesting to think about the possibility of switching back and forth. So you can turn the activity on, turn it back off, and sort of repeat this in different patterns, and you can actually get different types of behaviors this way. But that is something we haven't actually looked at explicitly. Not sure if I'm answering your question, but
Thank you, John.
thanks.
Okay. With this, I would like to thank Professor Gibbs once more for the very interesting talk. And we will move on to the next speaker now for the day. So the next speaker that we have is Professor Anirudh Mandal, who did his PhD in electronic science from University of Calcutta in 2008. After that, he has done his postdoctoral fellowship at IIT Kanpur and Dongkyung University, South Korea. He has joined the Department of Electronics and Communication Engineering, NIT Agartala, in 2010 as an assistant professor. From 2018, he's working as an associate professor at NIT Durgapur. And his research areas are one-dimensional metal oxide semiconductor synthesis by GLAD for application of UV photodetector, plasmonic detector, hybrid semiconductor detectors. He has several national and international projects. So with this, I would like to welcome Professor Mandal. Hello, sir. Professor Mandal?
Just a minute.
Yeah.
Yeah, I'm audible. Hello.
Yes, yes.
Okay, so I'm sharing my presentation. Okay, so my presentation is visible. Yeah, my screen is visible.
Yes.
Okay. Okay. So good morning to all. First of all, I must thankful to Professor J.P. Singh to give me the opportunity to deliver the lecture in the virtual platform in Nano GLAD. So today I'll just talk about the glancing angle diffusions of oxide semiconductor and its applications for the sensor. So this is the outline of my presentation. I will basically talk about the introductions of the one-dimensional nanomaterials and the applications of the materials for the different sensors, detailed fabrications procedure, and oxide nanowires as a photosensor, biosensor, and phase change sensors. That means the sum of the devices, as well as the heavy metal sensor. So this is the motivations of the one-dimensional nanostructures that we are using for the different applications of the sensors and the devices. You know, as we have moved from the bulk to that of the zero-dimensional structures, there are the several structures we get, the two-dimensional materials, the one-dimensional materials, and lastly, the zero-dimensional materials. Each and every cases, the materials has changed its density of the states, and according to the change of density of the states, the materials different properties like the optical properties, mechanical properties, and the electrical properties has changed. Among them, the one-dimensional materials are very, very important for the applications of different type of phase sensors as well as the optical detector and LEDs due to its unique properties of the electronic properties as well as the density of state changes as compared to the others. It has a high speed of the electrons from one end to other end by the applications of the potential from the outside of the materials, and it has the different properties of the optical which is completely different from the bulk and the 0 dimensions and the 2 dimensional materials. So that's why we have chooses the one-dimensional materials for the applications of the optical photodetector as well as different efficient sensors. So nanowires can be used as an anti-reflections coating. If you see the first cartoon into the right-hand side of the presentations, you can see there are the two types of the anti-reflections coating can be fabricated by using the nanostructures. One is the different orientations nanostructures, one-dimensional structures, and another is the perpendicular nanowires. So in the two cases, if you compare, the perpendicular nanowires are very much applicable for the absorptions of the photon inside the structure of the active media of the device, which can be generate the more electron pair, and therefore the efficiency of the device can be increased. In the case of the heterostructure based nanowires devices, we know that the device junctions areas are very short. So if the photon will be absorbed at the active medium of the junctions, then the electron and holes which will be generated due to the absorptions of the photons, they will be quickly separated into the electrode, and the efficiency of the device will be enhanced. In the case of the anti-reflection coating, we normally using the thin film based coating, which having which having a particular thickness to absorb a particular wavelength. So to absorb a wide band of the wavelengths in the solar spectrum, we need to fabricate the different thin films of the different thicknesses, and which basically enhance the cost of the devices. So if you can use the nanowire structures, so it basically provide you the different dimensions of the nanowires on the surfaces of the devices, and which can be tailed as a graded index media, and the graded index media having the advantages to absorb a long wavelength range from 400 to that of the 3 microns, so which having the advantages over the any kind of thin film based anti-reflection coating. So already we have some report on this graded index type of nanowire structures for the anti-reflection coating applications. So this is the one kind of heterostructure devices, heterostructure nanowire materials, which can be used for the high refractive index and the low refractive index. The idea was that, so if we can use this kind of anti-reflection coating, so having the low refractive index at the top and the high refractive index at the low, so it can be used to enter the infrared rays inside the room when it will be used as an anti-reflection coating on the smart window of the room. So it can be used to warm the inside of the room at the winter season. But if we can change this, can change automatically the refractive index of the media, so that on the summer season, the titanium dioxide having the high refractive index as compared to that of the vanadium oxide at the low refractive index. Vanadium oxide will act as an active media for the reflections of the infrared rays inside the room. In the summer season, it must be reflected out the infrared rays at the summer season. So inside the room will be the cool. So it is a very, very important thing if we can use the nanowire structures of this kind of things. So if you use the nanowires of the vanadium oxide, which is an active media and can change the refractive index with the temperature, so the nanowire dimensions of this kind of vanadium oxide will be changed in such a way. If we go for the low dimensional nanowire structures, the phase change temperature will be decreased, which is very, very important. This kind of structures can be used to fabricate the smart window, as well as this can be used to coated outside of the satellites, which can be goes for the upper atmosphere, where the changes of the temperature is very, very important to protect the all electronic devices. So this kind of phase change materials are very important, and if it is a nanowire vest, it is most important to protect the all electronic devices inside the spacecraft. Hello.
Yes, you are visible. You are audible. Yeah.
Yeah, but the slide is not changing. Yeah. So these are the different kind of the devices that we can basically fabricate with the base of the nanowire structures. Among them, nowadays we are very much interested to fabricate the biosensor based sensors, which can be used for the sensing of different kind of biospecies. Not changing actually. Okay, so these are the different fabrications procedure. We can use the liquid phase epitaxy, we can use the vapor phase epitaxy, MOCVD and MB technique, but these techniques are very much costlier. So we can go to fabricate the this kind of one-dimensional nanostructure by oblique angle depositions. With the help of the oblique angle depositions, we can very easily fabricate the nanowire structures. The detailed fabrications of the mechanism of the glancing angle depositions has been discussed in this content. So I am not going to detail of the fabrications procedures and this theory. You know, for the perpendicular nanowire structure, we must have to use the azimuthal rotations of the substrate as well as the sum of the oblique angle depositions. The combinations of the oblique angle and the rotations of the substrate will give you the perpendicular nanostructures, and it must be depends on different theories which has been written here. So I will directly go to the optical sensor fabrications techniques. So for the optical sensor fabrication, we must have to very much careful about the absorptions of the photon into the depletion region, as well as the separations of the electron hole pair generations when it will be absorbed into the depletion regions to the electrode. So basically, if you use a rectangular pulse of the opticals, so it will be the output pulse of the devices. So it will come into the electrical pulse, and this is the optical pulse which has been used for this kind of devices, optical sensors. So if the optical sensors, the junctions capacitance is very high, so it's very small, so it will basically give an ideal output of the photodetector. Will get an ideal output of the photodetector. If your C is very large, we'll get a tail like this. This is called a diffusion tail. And if you get a small V and a small W and a small C, so again you will get to near to the ideal photodetector. So according to this design, we have to make the photodetector which can be used, which can be worked as an ideal photodetector, and fast response can be obtained. In the case of the photodetector which has been made by the any kind of nanowires, having the very fast response as compared to that of the bulk materials which have been used for the photodetector fabrication, we have used the following procedures to fabricate this kind of photodetector. You can see the efficient cross-sectional images of these nanowires. So these are the nanowires which have been made of the titanium dioxide with the azimuthal rotations of 100 RPM. So these are the titanium dioxide nanowires directly grown on the silicon substrate. So this is the cross-sectional schematic diagram of the device. We have taken the P-type silicon, then N-type titanium dioxide thin film, on which a nanowire-based anti-fluorescence coating of the titanium dioxide, which has been used as an anti-fluorescence coating as well as the active region of the device. We use the gold as an upper electrode and indium as a lower electrode of this kind of device. We can see there are the two types of device we have used. One is the bulk materials thin film based, and another is the nanowire based. And nanowire based materials shows the better responsibility as compared to that of the thin film based devices. You can see the higher responsibility can be obtained from the nanowire based devices as compared to that of the thin film based. And this is the responsibility of the device with the light on off conditions. So this shows that the nanowire based devices having the higher responsibility as compared to that of the bulk one. So again, hello. So again, if you go for the another kind of nanostructures, which has been shown here, you can show that the two kind of devices we have fabricated. One is based of the zigzag nanowires. So zigzag nanowires has been grown by this way. Once we have deposited at phi is equal to 0 degree, then we have rotated is phi is equal to 180 degree, and then the depositions has been made. So we get the one structures in the right hand side directions and the left hand side, right hand side. So this is the zigzag structure. We have used this two kind of materials for the optical absorptions. We have seen the optical absorptions for the zigzag kind of structure is more. So idea was that the incident photon which has been lost due to the absorptions or the reflections from the silicon wafer directly, they will be absorbed into the active medium without losing any kind of photon inside of it. So we have since really these ideas worked out, and your absorptions of the photon inside this zigzag structure has been enhanced. So we have also seen the responsibility of the photodetector of this kind of materials. We have seen the responsibility of the photodetector of zigzag nanowire based has been more as compared to that of the normally nanowire based photodetector. We have also seen the responsibility is in the UV region, and there is a 4 times decrement into the responsibility into the visible region. We have also determined the different rise time and the fall time of the photodetector from this above experimental condition. So the silicon monoxide and titanium dioxide heterostructure nanowire based photodetector also has been fabricated. So in this case, you can see first we have deposited the silicon monoxide at the beneath, and on of that the titanium dioxide nanowires have been fabricated by glancing angle deposition techniques. This is the team images. You can see the fabrications of the SiOx and titanium dioxide nanowires from the color contractions. And we have seen this kind of nanowires are very, very important. We have seen that this kind of nanowires are very, very important for the fabrications of the junctions less LED, because the titanium dioxide and the SiOx having the several defect states. So when it has been excited from the outside, the titanium dioxide having the electrons which goes to the conduction band, and the conduction band electrons started to move to the silicon monoxide side, and they will be recombined with the capacities at the junctions of the silicon monoxide and titanium dioxide, and they will be radiatively recombined, and the photon has been generated. So this shows from the PL curve how the photon has been generated more. And then we have annealed the samples. Due to the annealing of the samples, the defect states between the silicon monoxide and the titanium dioxide has been decreased, and due to the decrement of that, the PL intensity has been decreased, which is shown from here. And this kind of materials then is very much applicable for the photodetector. So we have seen the photodetector, which is annealed, is more responsive than that of the as deposited samples. So these samples shows the different new kind of transitions between the conduction band and the valence band, which has been described here. So we also have fabricated some of the titanium dioxide and copper monoxide or cupric oxide based nanowires. So we have taken the silicon substrate, we made the silicon titanium dioxide thin film on which the copper cupric oxide nanowires has been grown by the glancing angle deposition techniques. And this kind of photodetector has been used for the self-powered photodetector. You have seen we have generated the photons, electrons and photons, which has been quickly separated to the electrode at the 0 volt. The applications of this kind of photodetector can be used for the robotics eye applications. So we have since also the photo responsivity at the applied threefold for the several wavelengths for the wide wavelength range. So which is also can be applied for the multi-band photo detector applications. So humidity sensor, we have also fabricated some humidity sensors. You can see it from the from here. We have fabricated the silicon monoxide and the indium oxide heterostructure based devices. So where it can be worked as a 2D sensor and 2D like sensor. So we have immersed these devices into the water or the moisture, and we have seen the band gap of the total devices has been changed, and the change of the band gap from obtained from the reflectance measurement of the materials, and also we have used the different humidity percentage to detect by the devices. We have seen as the humidity has been enhanced inside the chamber, the current conductions of the devices has been enhanced. We have used some theoretical approach to find out the or to determine the change of the band gap. We have since the change of the band gap for the both of the cases, theoretical and experimental, is nearly equal, and it is just 31 nanometer and 33 nanometer has been calculated, and the changes of the conductivity has been measured for the up to 99% of the humidity, which has been changed from the 55% humidity into the materials, and this has been due to the absorptions of the water at the junctions of the silver and the indium oxide. So the biosensor, we have used this photo detector as a biosensor. We have used the two different kind of structures. So first structures, we have used the titanium dioxide nanowire based MSM photo detector, and second we have used the plasmonic based MSM photo detector. The figure B is shows here the top view of the electrodes that we have used. We have characterized this photodetector for the different wavelength, and we have since this photodetector is more responsive at the UV region, and we try to measure the glucose by using this photodetector. You have since the arrangement of the measurement here in my laboratory, and we have tried to take the glucose mixed into the water, and we have since with the increasing glucose concentrations into the water, the conductivity of the current of the device has been enhanced. We have characterized for the 6 months to find the stability of the devices. We have since the stable measurement for the devices. We are trying to fabricate an enhanced photodetector which can be used directly the blood sugar of the human body without doing any pain for extracting the blood from the human body. So we have also developed some vitamin D sensors. So here we have used the AG nanoparticle based titanium dioxide sensors, nanowire based sensors. Everything is deposited by the glancing angle diffusion techniques. So we have since the photodetector is very much sensitive into the UV detector, because the vitamin D having the absorptions bands into the UV region. So we first check the stability of the photodetector in the UV region. You see from this the characteristics we have done into the UV region, and then this is the absorption characteristics of the photo this vitamin D, which is dissolved into the methanol, and the photocurrent which has been determined for the vitamin D at the deep UV and the UV region. We have since a clear enhancement of the current of the photodetector by due to the presence of the vitamin D inside the methanol. So we have measured the several characteristics for the different concentrations of the photodetector of the vitamin D into the ethanol, and we have seen that the responsibility of the photodetector due to the different percentage of the vitamin D is different. We have calculated the LOD and LOQ of the photodetector, and we have since this kind of photodetector is very much applicable of the vitamin D into the methanol as well as into the water. So vitamin D is a very important factor for ADS because it is initiate the all kind of diseases in our body. So early detections of the vitamin D is very important, which we have done by using this kind of optical photodetector. So we also have used the nanowire-based nanowire-based FET. We have fabricated the nanowire-based paste into the gate, and we try to determine the arsenic, which is a heavy metal, and as well as the glucose. So, we are going to directly to the phase change materials. So in the case of the phase change materials, what we have seen we have fabricated the vanadium oxide nanocrystals, and we have coated these vanadium oxide nanocrystals by the titanium dioxide thin films. The idea was that the vanadium oxide, which is grown by the different techniques, has changed its phase due to the reactions of the atmospheric oxygen, and due to these cases, the vanadium oxide, which can be used for the different purposes of the phase change materials, cannot give the stable performance at all. Therefore, we have used first time the titanium dioxide coating on the vanadium oxide for the stable determinations of the phase change of the materials with the temperatures. So we have seen here, this is the cross-sectional view that we have shown here. So we have first taken the quartz plate, quartz substrate, and on the quartz substrate we coated the aluminum, and after that we have fabricated the vanadium oxide nanowires based or nanocrystal based one-dimensional structures on which we coated the titanium dioxide. Titanium dioxide is a very stable material, so it has been coated the vanadium oxide from its environmental oxygen reactions. We have put the two electrodes at the top, and we have measured the electrical characteristics of the vanadium oxide nanocrystals and titanium dioxide heterostructure-based samples. We have seen a clear changes of the phase from the semiconducting to the metal at nearly 60 degrees, and this change also will be stable after the 1 or 2 months. And we have used some theoretical approach to calculate the different kind of characteristics of these materials, and we have seen these materials are very much applicable, and we have obtained the small radius polarity model to find out the resistance at the different modes in the semiconducting and that of our metallic phase. And also we are newly determined the concentrations of the materials, the electron concentrations of the materials in the semiconducting phase and the metallic phase, which is the unicity of the model, theoretical model that we have determined here. So in the next phase,
Professor Mandal?
Yeah, just a minute. I'll go to my conclusions. So we also have fabricated the FET for the glucose and the arsenic sensors. So this is the FET sensors where we have used the source and the drain, and in the channel we have used this kind of nanostructures, and these nanostructures are used for the to mobilize the any kind of biosensor. We have used this kind of nanostructures of the FET nanostructure based phase for the glucose sensors. So we have since a very clear or state enhancement with the enhancement of the glucose sensing. So we have started from the 40 to 200 mg per DL. We have seen the clear enhancement of the characteristics of the FET, and this is for the room temperature and the 50 degrees C characteristics of the FET, and this is for the arsenic, and arsenic determined by the FET sensor. And I must thankful to my PhD students and to the major projects that I am running at NIT Durgapur, and the instrument that I have procured for the different fundings. And thank you for the glancing and the diffusions which I have set up in my laboratory for doing the all kind of research. And thank you to Professor JP for giving me this opportunity.
Thank you, Professor Mandal, for your talk. Maybe we'll just have one or two quick questions. Yes, Dr. Mukesh.
Hello.
Yeah,
Yes, a very good talk. So I have a question on this TiO2 based UV photo detector.
right.
So like the time response is in seconds actually.
Yeah.
So what do you like see the reason for this time response and how we can improve it further?
Yeah, it's a very good question. So first of all, if you see, I have determined, I have made here a photo detector which is shows the vertical response. But if you can do MSM time photo detector with that help of the titanium dioxide, or the nanowire will be the active medium, then it will be improved. So already I have experimented that I improved the photo detector responsibility with that help of. And also the second thing is that that photo detector has been made by the titanium dioxide, which is not annealed, as deposited titanium dioxide has been used for the making of the photo detector. So if you annealed and can make the titanium dioxide the oxygen defect free, then it can be improved, definitely improve your photo detector response time. Definitely, it was a very large response time that I have shown in my presentation.
Okay, any other question? Okay, with this, then I would like to thank Professor Mandal again. Thank you, sir.
Thank you.
And we'll move to the next speaker. So you have to stop sharing the screen,
Yeah,
Professor
yeah.
Mandal. Yeah. So the next speaker that we have today is Professor Huang, who obtained his PhD in Science and Engineering of Materials at Arizona State University. After working as a postdoctoral fellow in Department of Electrical and Computing Engineering at University of Alberta, he then joined the Department of Physics at Hong Kong Baptist University as an assistant professor and was promoted to associate professor in 2015. Dr. Huang is an associate director in Golden Meditech Center for Neuroregeneration Sciences at HKBU and is also the member of the Hong Kong Young Academy of Sciences. He serves as vice president in Hong Kong Materials Research Society. He has contributed to 2 book chapters and published his studies in high impact journals like Nature Materials, Nature Nanotechnology, to name a few. Dr. Huang was awarded with outstanding research achievements such as the Professor Rudolph A. Marcus Award, the Incentive Award for Outstanding Research Achievements, and National Level Technology Project Award for Advanced Individual. He's serving as a review editor for Frontiers in Chemistry, associate editor for Sciences, Science Advances Today, and Science Letters Journal, published by Cognition. So here I welcome Professor Huang. Over to you, sir.
So thank you, Chairman. And I want to thank Professor Singh and Professor Zhao for the kind organization of such a wonderful workshop. So first of all, may I know that did you see my full screen?
It's visible.
Sorry,
It is visible.
it's invisible right now.
We
The
can
first
see.
we can see.
It's
We can see.
visible.
So you can see my full
Yeah.
screen of my presentation, right?
Right.
Yes.
Okay, okay. No, thank you. Yeah, so so here I want to introduce you the current research progress in my laboratory. So we use GLAD to apply it into the 3 quite interesting research area. So I think I don't need to spend too much time to talking about the GLAD. And so the first character is we can organize the shape of our structure, right? So I call this is a sculpture nanoforest or SNAF. And the materials is engineerable as well, right? So I think everybody recognize these data published by Pierre Fischer's group. So right now, the guy can fabricate the inorganic materials, and this is the heterojunctions, right? And as well as the coherent structures, as well as the arrow. So that it's fantastic. So we use GLAD, and we studied in the three main directions. The first one is the chiral nanoscience, and the second one is optoelectronics, and the third one is related to the bio system. So that is cell culture. And today in my talk, I want to tell you the three stories. So the first story is about the chiral nanoscience. So I want to show you how we use the metal to control the molecular chirality. So I think most of you is not familiar with the chirality. Oh, sorry. What happened? Sorry about that. Where is my T? So now, can you see my PPT again?
Yes, Professor, it is
Okay.
visible. Yes.
Yeah. Okay. So, so what is chirality? So when we have an object, their mirror image can be superimposed. So that is non-chiral structure, right? So when the object and their mirror image cannot be superimposed, and they are chiral. Right? So molecule have chirality, and the most common chirality is the carbon atoms undergo the sp3 hybridization. And when they have the four functional group, and these four functional groups, they are totally different. And this carbon, we call it a chiral center. So this is the point chirality. And besides that, we have axial chirality, planar chirality, as well as the helical chirality. And in the nature, there's a very interesting phenomena, which what we call is a homochirality. So for example, amino acid, that is the life building block. So we have 21 amino acid. So except for this molecule, the rest of the 20 amino acids, they are chiral. And in the nature, we can only find a left-handed amino acid. There, you cannot find the right-handed amino acid. And this is what we call homochirality. And the homochirality is the very important character in our body because amino acid gonna assemble it into the peptides as well as the different hierarchy structures, right? So our biological system have homochirality, right? And their biological process and functions, they're going to be very sensitive to be dependent on the structure, on the chirality of molecule. So here's one example. So this is the drug, right? So for the right-handed, the lidomide, they're going to be function as the sleeping drug for the pregnant women. However, his mirror image gonna cause the very serious side effect, right? The baby gonna have missing or non-normal arms, arms, legs, etc. So I just want to show you this importance, how important we need to control the chirality of the molecule. And that is what we call asymmetric synthesis. And of course, chemistry, chemist has invented a different kind of methodology, right, to manipulate the molecular chirality. And but here, what I want to say is, in the nature, we know that, right, when we can rotate the crosswise and counter crosswise, and we can generate the helical structures. I think everybody have done the GLAD, we know that. So now the question is, can we directly use this microscopic rotation to manipulate the molecular chirality? But we know that, right, the dimension scale, there's a big gap, right? The microscope rotation, right, is in the visible region is very big, but the molecule is at the molecular scale, right? So there is a big gap. So how we can do that? And actually GLAD can help us to do that. So what we are doing is, first of all, everybody know that, right? We can rotate the substrate crosswise, counter-crosswise, and we can have the chiral nanohelical structures, right, which has been reported by Pierre Fischer in 2013. And then we use this nanohelical as the photocatalyst. So we put the molecule on the surface under the light, and we can control the product, the chirality of the molecular product. So that is our idea. So here is the example, and hopefully you can see this molecule in my hand. Yeah. So this molecule we call it an AC molecule. It's a Prandtl molecule, right? And it's a function is terminated by the carboxylic acid group. And we need to have the two molecules. And these two molecules, when they form a dimer, and they're gonna have a silodimerization. So we're gonna have 4 products. But because we have the photocatalyst, and this is made of the silver, so we will not have product 1 and product 2, but we have product 3 and product 4. For the product 4, they do not have chirality. So now let's take a look at the product 3. So I directly give you the conclusion is, when we have the counter-crosswise substrate rotation, we're gonna generate the left-handed nanohelical structures. And on the left-handed helical structures, this molecule have 2 faces, right? The one I painted in green, the other one is purple. So on the left-handed surface, they're gonna have the purple to purple stacking. So they're gonna generate the +3 chiral molecules preferentially. So if you rotate substrate crosswise, and we're gonna generate the right-handed nanohelical structures, and on the surface, the molecule preferred to have this green-green stacking. So they're gonna generate these negative 3 chiral molecules. So this is the conclusion, and I show you the result, right? So this is the left-handed silver, right? And this is the HPLC, right? We have the +3 and -3 products, both, but we calculate the integration area of the peak, and then we calculate the EE value. So based on this formula, when EE value is positive, which what we found here, that means that we prefer to generate the +3 molecules. And on the left-handed silver nanohelical structures, you can find that the -3 is more than +3, right? And the EE value is negative. However, the EE value is not high, to be honest. So we change the pitch of the silver nanohelical structures from 8 nanometer all the way to more than 200 nanometer. And the common result is for the left-handed silver nanohelical structures, the EE value is positive. That means we preferentially to generate the +3 molecule. And on the right-handed, the EE value is negative. And we have generality. So the copper can also function as the photocatalyst, right? The left-handed, the EE value, they are all positive, and the right-handed, the EE value, they are all negative. And we have a control experiment, right? So rather we use the helical surface, right? We generate the silver tilt nanorod, so they do not have chirality on the surface. And we very excited to find that, right? The EE value is equals to 0. Right, so that demonstrates that chiral surface really played a very important role for this asymmetric synthesis. So why we can get that? Because when we do the high resolution DEM, we found that, for example, on the left-handed silver nanohelical surface, on the surface that have wave-light chiral surface, and this is at the atomic scale. So we do the simulation, we find that for this green-green phase stacking, they have the lower surface energy, right? And they're gonna generate the -3 molecules. But for the purple to purple stacking, the energy is higher. So just because of that, right, for the right-handed surface, they prefer to generate the -3 chiral molecule, right? And for the left-handed surfaces, the result is upside down. So this is the reason. Okay. Yeah. So we just give a proof of concept that we can control the chirality at the molecular scale by using the very simple microscopic controlling of crosswise and counter-crosswise rotation. And how we can do that, because we need to use the metal narrow helical structures as the medium. And actually, not only use the light. Right now in my lab, we are working on the heterogeneous asymmetric synthesis in the solution as well. Okay, so this is the first story about the chiral nanoscience. And actually, because of the time, I cannot go deeper. But currently, what we are doing is we try to synthesize the alloy chiral nanoparticles, and in order to control and enhance these asymmetric catalysis. So my second story is the optoelectronics devices. And actually, yesterday, Professor Kim, excuse me, Professor Kim already introduced his very interesting topics, how to use the nanopillar array to function as the optoelectronics devices. And here, what we are focusing on is the Perovskite solder cells. And I call it is the PSC. And a nanopillar array, which is vertical, they're going to function as the charge transporting layers. So, for example, we synthesize the nickel oxide. These function as the whole transporting layers, and we can get the pretty good photo to electronics conversion in the perovskite solder cells PSE. And we also use the TiO2, titanium, which is metal, and the tin oxide, which function as the electron transporting layers, and they can also have a pretty good photovoltaic performance. And we just start to study optoelectronics 2 years ago. And because of time, I cannot go into the detail, but what I want to emphasize here is, rather we studied the rigid PSC, we were more interested in the flexible PSC, because the wearable technology can have a huge demand, actually. And so within the past few years, right, the development of flexible PSC has been found very quickly, right? And towards the product, there's several problems that scientists need to focus on, right? The first one, this is the flexible PSC. So how about the mechanical robustness? That is the one issue. Another one is the environmental stability and the manufacturing cost, large area fabrication, right, as well as the lead-related toxicity, right? People want to use the lead-free perovskite, right, to enhance these environmental pollution issues. And so what the GLAD can do towards to solve these 5 problems, of course, GLAD is not Superman, they cannot solve everything. And very interesting, we found that it seems like to use the GLAD, use the nanopillar array, we towards to solve the problem of the mechanical robustness and environmental stability. So I just want to spend a couple minutes to talk about this. And so first one example is nickel oxide. So the nickels are going to function as the whole transporting layers, right? And this is the flexible PSC, right? And we can do the large area deposition. Of course, I think everybody know that. That is the one of the advantage of GLAD, right? So, and let's take a look at this scheme. So mechanically, we bend the flexible solar cells, right? And we measured the PCE, right? This is the photo conversion efficiency, right? And we found these nanopillars. So let's take a look at the black curve. Right? After 500 banding, the PCE has been degraded roughly 40%. But when we have the nanopillar, right, the PCE only degrades around 15% after 500 banding, right? So mechanical robustness has been significantly improved. And the reason is we found a nanopillar, right? You can see the very big crack. And after the simulation, we found that actually the nanopillar can release this mechanical stress, actually. And not only the whole transporting layers, right? We use the tin oxide as the electron transporting layers. We can also find this phenomenon, right? For example, this is the environmental stability. So we shine a light in after 200 hours. So this one is without nanopillar, right? We spin coating the tin oxide onto the PSC, and you can find that PCE reduced 40%. But if we use the nanopillars, right, even up to 800 hours, right, the PCE only reduced 90%. And what I want to emphasize is this one do not have encapsulation; it's exposed in the air. And of course, the mechanical robustness has been significantly improved. And you're gonna ask me why, and to be honest, we don't know yet. And actually, we are collaborating with the colleagues in Hong Kong, and we towards to solve these problems. So why the nanopillars can enhance the environmental stability, the mechanical robustness of the flexible PSC. Okay, so yeah, I still have 8 minutes, so I want to tell you the third story, which is related to the cell culture. So we have spent more than 7 years working on this project, and we have only 1 publications. Unfortunately, this is a long way to go. And so what we want to do is we have some stem cells, and we put the stem cell on it. We want to differentiate the stem cells to get some functional cells. So that is basically the idea. But before talking about the project, I want to tell you so why I want to do this. So stem cell therapy, right, is a very important therapy because currently we have a lot of disease which cannot be cured, right? And the stem cell therapy is promising methodology. So people need to have the stem cells, and we need to make the cell culture, and the stem cell can differentiate into the different functional cells. And after we get these functional cells, we can put these cells back into the human body, right? So this is the cell regeneration, right? So they have the possibility to cure some incurable diseases. So that is the stem cell therapy idea. And for the stem cell therapy, cell culture, of course, is one of the important process, right? And what I want to emphasize is stem cells can differentiate into different cells, right? But we want them to differentiate, to specifically to differentiate into a particular cells because we want to treat a particular disease, right? So this is the idea. So how we can do that? And this is one thing in specific differentiation. This is one problem. And the second problem is we want to cell differentiate as quickly as possible. So in order to solve these 2 problems, traditionally, what the doctor do? The doctor adds a large amount of additional growth factors, right, to make this differentiation as quickly as possible, as specifically as possible. But they're gonna give us the very fatal side effects. For example, they're gonna cause the tumor, they're gonna cause the cancer. So for the FDA, they gonna if we use a large amount of growth factors, it will not be applied to clinical trial. So that is the problem. So in order to solve this problem, the scientists are very smart, right? So they generate this extracellular matrix, right, to differentiate the stem cells, right? So this is like the 3D structures, and nanopillars is another option. So obviously, GLAD can do something here because GLAD, right, we can generate the nanopillar array, right? We can differentiate the stem cells. But so our invention is we generate the ZZ structures, basically, and we put the neuron stem cell on it. We demonstrate that we use a minimum amount of growth factors. And we can very quickly and we can very specifically to differentiate the neural stem cells into neurons, right? And so you have possibility to treat the Parkinson disease. So this is the background. So why we want to do this. So the next, before I tell you some experimental results, so please take a look at this video. Sorry, I want to ask, can you hear my video?
No.
No? Oh, so that's gonna be a problem. Yeah, if you cannot hear, maybe I want to skip this video, but basically the video just, or maybe I also show the video how we do that. So here, we just tell you how the general cell culture is doing, right? They need to add a lot of chemical factors. And this is our invention. Right, so in my lab, right, we use the glassing angle deposition, right, and we fabricate the zigzag structures. And I think everybody know this. And this is made of silica, so it's a biocompatible materials. And then this is my collaborator, Professor Kenyo, in biological department at HKBU. Right, so they put the neural stem cells on it, and then they do the differentiation. So the ZZ structures, just like a matrix, and the neural stem cells sit on it is very uncomfortable, so they try to differentiate into the neurons. Yeah, and we just transplant these differentiated neurons into the Parkinson disease rats, and after several months, and we find that the symptom can be released. Okay, so I'm almost run off to my time, so I very quickly go through some experimental results here. So for the comparison, we synthesize the helical as the ZZ, and this is the silica. So for the first week, right, we do the comparison. Control is we found it's on the glass, right? And this is the nanohelical, this is the ZZ. The conclusion is, compare with these two, the nano ZZ, right, they can differentiate the neural stem cells the most quickly. And the same conclusions we can draw for the 2 weeks. And we found that they have a very close contact of the differentiate cells onto the ZZ. And biologically, we found there is a 4 biosignal channels to direct the neuron stem cells into the neurons. And we found that the ZZ, they can activate all these 4 biosignals to produce the neurons. And then we put these differentiate neurons into the rat. So we found the neurons, right? This Parkinson rat, they can spin round and round. That is the simpleton. But after 2 weeks transplantation, you can find that the spinning has been released. So we got the pattern from US. We got the medal from the Geneva in 2018, and we got the Tech Connection Innovation Awards in 2019. Yeah, so that's it. I just tell you the 3 stories about chiral nanoscience, optoelectronics, as well as the cell culture. And I want to appreciate my group members, my collaborators, and the funding from Hong Kong and mainland China. So at the end, I want to appreciate your attention. Thank you, and I'm very happy to answer your questions. Thank you, Chairman.
Yes, thank you, Professor Huang, for a very interesting talk and the 3 stories that you have told us all. Can we have some questions now? Yes, Dr. Dhruv. Dr. Dhruv Pratap Singh. I think the host has to unmute.
Hi, Dr. Dhruv, you have to unmute yourself. I have sent the request.
Okay. So,
yes.
Hi, Professor Zhuang. I must say it's a very nice talk. I really enjoyed it. So I have 2 questions. First is when we see the adsorption of chiral molecules on the helical structures, then do you think the structure size like a page or the diameter of the structures will play some role there?
Yeah, yes, exactly. So,
and also the material, sorry.
Yeah. So 2 questions. The first one is the size. Yes, and so let me share this screen here. Yeah. So let's take a look at this table. Actually, if we consider the pitch, for example, 230 nanometer, right? So this helical structure is actually is very big, right? Which will be not visible by the molecule. But when you zoom in into these surface, they have chiral lattice, which because we rotate the substrate when we do the growing. And so this chiral phenomena actually it's at the atomic scale. And so we can control the absorption format of the molecule. And actually, we need to, when we reduce the pitch as small as a nanometer, and you can find that the EE value have a little bit increased, right, from the 1.9 to 4%, right? If you take a look at the right-handed, right, the EE value going to increase from the minus 2.6 to minus 5.4. And we do the GLAD, we know that you want to reduce the pitch, that means you need to increase the rotation. So when you increase the rotation, the chiral surface, the percentage of the chiral surface is going to be increased, right? So we can have the larger EE value. So the structure actually is very, very important. And the second question is about materials. And so for this molecule that have carboxylic acid group, So we need to have a surface, and this surface can have self-assembly of the molecule, right? So the normal metals, basically, it cannot work. And actually, there is additional effect we already discussed in the paper is about chiroplasmonics. So we know that the silver, right, the LSPR happens in 360 nanometer,
Yes.
right? And for this photosynthesis, the excitation actually is a 365 nanometer. So the resonance. But if we use copper, the chiroplasmonic is going to happen at 600 something nanometer, right? Which is out of resonance. So the chiroplasmonics may have some contribution when we use silver, but for copper, they may not have chiroplasmonics effect. So yeah, so this is
Or
what we consider.
yeah. Or
The
maybe we have to move to
materials.
the higher wavelengths.
Yeah, and so that means we need to select the different chemical reactions.
Okay.
Yeah,
Okay.
yeah, exactly.
And for this intracellular matrices, for the cell culture, you
Mhm.
used only the zigzag or chevron-like structures. So was there any reason behind this? Or we can also use the helices or the vertical rods or slanted rods?
Yeah, that is a very, very good question. Actually, what we are doing is we compare the zigzag with helical, with vertical posts, and for especially we want to if you want to differentiate the neuron stem cells to neuron, we need to use zigzag. But right, the stem cells can differentiate into different cells, and maybe the different shape can work for the different functional cells. And so we have a spin-off company, is MetaCell, and actually we are working on this right now. So this is our first product. The target is Parkinson's disease. We want to get the neuron, so we need to use the zigzag. So for the different disease, maybe we should use the different shape or even different materials as well.
Okay, thank you.
Yeah, thank you.
Okay, with this, I would like to thank Professor Huang. And for any further questions, kindly use the chat box. To keep the time of the session, we'll move to the next speaker.
Okay.
Thank you, Professor Huang. Yeah.
Thank you. So maybe you stop sharing. Thank you.
Yeah. Dr. Shashank, can you please give me the rights to share the screen? Okay, you have already shared. Thank you. So we next have Professor A.R. Gonzalez Elipi. He is research professor of the National Research Council of Spain and working at the Institute of Materials Science of Seville, Spain, University of Sevilla. He has been the director of the said institute and responsible of the Materials Science and Technology area of CSIC. He received a PhD from University of Madrid and has been a postdoctoral researcher and visiting fellow at numerous universities and research centers in Europe. He is currently responsible for the laboratory nanotechnology on surfaces and plasmas at the ICMSE. His current research interests focus in the domains of thin film and surface nanotechnologies, plasma catalysis, advanced surface characterization, and functional materials. He holds numerous patents resulting from these activities. He has been chairman and member of scientific committees in numerous conferences and symposia and imparted numerous conferences. Over to you, Professor Elipi.
Okay. Good morning. Can you hear me?
Yes.
Okay. So I would like to share my screen. Okay, compartir here. Can you see my screen?
Yes, we can see.
Okay, perfect. So good morning to everybody. So let me first of all, thank the organizer for giving me the opportunity to share our research in this very interesting symposium. In my presentation, I will put the accent not on the application, but on the processing technique, and particularly in the use of magnetron sputtering in an oblique angle deposition configuration in order to control the nanostructure and to produce new nanostructure. So in part, this work is the result of a collaboration with a German laboratory in Dresden, particularly in what it is concerned with the acoustic wave activation of the position process. Well, for this audience, it is very well known what does it mean GLAD or oblique angle deposition. It concerns with the use of a substrate in this configuration, and using that, what we know is that we obtain these tilted nanostructures characterized by this nanocolumnar structure produced by this configuration. So if I have to stress two basic principles that control this growing mode, I would consider that they are controlled basically by two physical principles. On the one hand, geometry, as it happened with this very nice painter of Kandinsky, and shadow, as in this very nice picture of Edward Hopper. So taking into account these just two basic principles of controlling the growth process, what we obtain is this very nice nanocolumnar structure where we can control the porosity, the tilting angle, and also perhaps the lateral association of nanocolumns. Well, this is very well known, and this symposium has shown many applications of this type of nanostructure. But my point here in this presentation is well, these are other examples that can be obtained just by controlling the geometry, the helix, the zigzag, etc. And this had produced the possibility to go through many different applications. Well, this is just a table taken from a review paper we wrote some years ago. In blue, there are some of the applications to which we have applied this glancing angle configuration using the electron beam evaporation technique, which and this application covers a lot of areas of scientific and technical interest. But my point here in this presentation would be different. What happens if, in addition to the geometry, to the shadow, we incorporate another principle of modifying the growing process, dead scattering? So what happens if we incorporate some kind of mist, as in this painting of William Turner? In other words, what happens if we proceed in a magnetron sputtering facility where, besides controlling the tilting angle of the position, we have something which is very typical, very characteristic of this technique, and is the fact that we have gas here in the between the target and the substrate. Well, in principle, the answer to this question is known by this audience. In principle, you can control the nanocolumnar structure and get this tilted nanocolumnar thin fields, but there is many stories that should be bear in mind in order to properly control the deposition condition. So we have done this and applied this principle for different applications. I will not go today through this application, but just to mention that the results can be quite equivalent or even better using magnetron sputtering in comparison with electron beam evaporation. For example, for the production of cholesterol biosensor, producing a sensor for electrochemical detection of glucose, fuel cells, anode for fuel cells, water electrolysis electrodes, photonic mirror, electrochromic cathode, antibacterial layer for implants, lithium batteries, and many other applications. As I said, my interest here will not be focused on this application, but rather on the characteristic of the deposition condition using magnetron sputtering technique. And it is clear, if we consider the characteristic of electron beam deposition and compare them with a magnetron sputtering configuration, there are substantial differences. For example, in evaporation, we usually utilize a punctual sur, while in magnetron sputtering, the sur is not punctual. Here we don't have any plasma. Here there is no gas. Here we have a gas, we have a plasma between the target and the substrate. In electron beam evaporation, the energies of the evaporated particles is in the order of 0.1 electron volts, while the typical energies in a magnetron sputtering experiment range between 1 and 10 electron volts. And most importantly, while here the mean free path of the particles is practically restricted because we don't have any gas in the chamber, in this other situation, the mean free path is much shorter. Well, this brings me to the outline of my talk, in the sense that I will talk about the effect of the thermalization degree of the particles. I will talk about the energetic of the impinging particle, and in my last part, I will comment about the plasma substrate interaction induced by acoustic wave. Let me go very fast through the collisional transport in magnetron sputtering. In magnetron sputtering, we have three different types of particles: those which can be considered completely thermalized and that we arrive to the substrate according an isotropic momentum distribution. We will have ballistic species, ballistic particles, which do not change their trajectory, and these are typically used for glancing angle deposition. And we will also have particles which are partially thermalized and that will still preserve some of the momentum distribution that they have when they originate in the target. Actually, these two particles are those which are responsible for the oblique angle deposition structure that we are interested in. This is a work already a little bit old, some years ago, where we study the effect of the thermalization degrees of the particles and the deposition angle during an oblique angle deposition experiment using gold. And we produce a kind of calculated phase diagram. We also use a deposition model, and we discovered that depending on the situation in this diagram, it would be possible to get a compact structure like this one. A structure where in this area where we have pores which are moving from the substrate up to the surface, but not still nanorods. Or in this area, we have formation of nanorods. So it's very critical in this phase diagram moving through the thermalization degree and through the deposition angle. Well, in this area, we get the typical Thornton model structure, typical of magnetron sputtering deposition. Just to show you here the result regarding the effect of the deposition angle. We can, even if we have a similar thermalization degrees here, we can move from this situation to this situation where we have a completely tilted nanostructure. Well, this is the experimental and this is the simulation by Monte Carlo simulation. And you can see here that indeed moving through this area is very critical. So increasing the tilting angle is very critical to get the nanocolumns. However, if we move in this area where we keep the same deposition angle, but we move along the thermalization degrees, you can see here that we can move from this situation to this one, which is the one which is typically considered of a oblique angle deposition regime. But if we don't control sufficiently well the thermalization degree, we will get this other structure that you can see there. And these are due to this difference between the transport properties of the particle between the target and the substrate. Thermalization degree is important, but also the energy of the deposition particles. Well, this is a simulation, electron microscopy characterization and electron beam evaporated titanium. So you can see here that this is the typical situation when we work with a punctual source as an electron beam deposition. However, if we do the same experiment in magnetron sputtering, what you can see here is that we get nanocolumns when we work at very tilted angle, but nanocolumns which are completely different than the nanocolumns that we obtain by electron beam evaporation. Well, I cannot go into details, but the question is that in this and in many other situations where we have particles which has a certain energy above a certain energetic threshold on the surface, particles arriving particles may induce mobility of the atoms, either from the what we call kinetic induced mobility of the atoms or some bias diffusion. And modeling this effect in magnetron sputtering situation, what we can reproduce it perfectly well this nanostructure. What we have labeled this process as a kind of dragging mechanism in such a way that the energy and momentum brought by this sputtered atom arriving to the nanocolumns produce a certain increase in the upright direction of the nanocolumns. And also, as you can see here, a change in the width of the nanocolumns. Not only this change, also the density, for example, change, and many other properties. The point that I would like to emphasize here is that playing with this other parameter that offers you the magnetron sputtering situation make it possible to control other feature of the nanocolumnar structure typical of oblique angle deposition. Just as example, I cannot go into detail, but for example, these are a two-scale range of tungsten nanocolumns. Look here that the separation between these nanocolumns is 1.5 microns. Between these two, and this is possible because we have a very strict control of the position condition of this nanostructure formed by very wide nanocolumnar structure made of nickel zirconia structure. Of this, what we call Ito walls, decorated with gold nanoparticles, where the distance between these walls here is some 100 nanometers, and the size of the walls is some microns. As I said, I cannot go into details because I would like to concentrate in the last part of my talk, which is directed to the possibility to produce some 2D surface patterning using magnetron sputtering deposition. In terms of the story of art is the idea of getting something similar to the Vincent van Gogh painter, The Chief of Wit, having something of that kind, working with magnetron sputtering and the activation of magnetron sputtering with acoustic wave on propagating on the surface of substrate. Let me say a few words about piezoelectric materials and acoustic wave. A piezoelectric material, everybody here knows that is a material that can propagate and can induce acoustic wave in such a way that there is a displacement of atoms at the surface of the material. There is lattice deformation extending to some tenth of nanometer. And depending on the activation procedure that we are used, the wavelength of this wave which move along the surface of the piezoelectric material can range from millimeter to some 100 micrometers. Not only that, this deformation of the lattice are accompanied usually by some electrical polarization effect that, as you will see in a moment, are very important for our purposes. There are several types of acoustic wave. the so-called plate waves when we have a plate of a piezoelectric material, or the surface acoustic wave, the so-called Rayleigh SAW wave that affects exclusively to the surface. The experiment which I am going to show you here correspond to experiment carried out with plate waves. Our intention, of course, is to move to Rayleigh wave and to work with thin films technology. But at the stage of our research, we are still working with land wave and plates, piezoelectric plates. Well, let me show you the experimental condition of our experiment. We have a target. We have a piezoelectric substrate here, which form a certain angle with respect to the tracking of the track of the magnetron sputtering source. Of course, everything I have said about the control of the pressure in order to control thermalization, pressure and target substrate distance has to be very carefully controlled to get a good result for this experiment. I will not go into this detail, but just bear in mind that that is very important. Otherwise, we will not get the result which I am going to show you. Well, this is an skin of the experimental device. We have a lithium niobate substrate with 2 electrodes. We have some pin here to produce the excitation. And in this particular case, one of the resonant frequencies of this lithium niobate piezoelectric crystal is around 3.4 megahertz. Well, if we use not an oblique angle deposition configuration, but a normal configuration, we obtain a thin film that just by eye, we can see already some fringes, some difference in the contrast. And if we look this with a confocal microscopy, we can see that there is a difference in the flatness of the film. Well, the differences are not very important, but you can see here that, for example, here in the valleys, we have a thickness typically of 390 nanometer, while in the hills, we have a little bit higher thickness. We have crystallization. This is TiO2, which is rather unusual to get a crystalline form of titanium dioxide by magnetron sputtering at room temperature. So we see some difference, but the difference are not dramatic. So we are indeed producing some densification in these areas and less densification in this area. But of course, magnetron sputtering in a normal configuration is a typical technique to produce compact thin films. So we cannot expect too many changes. However, if we made the experiment in an oblique angle configuration like this one in this historical presentation, what we can see here is that actually there are a surface where we can see very clearly, even with the eyes, a 2D pattern of the structure. If we look in detail to the optical property in this point or in this point, we can see that actually the reflectance is completely different. So we have domains with quite completely different optical properties. If we look to the microstructure with electron beam microscopy, what we can see is that we move from this area to this area. We are moving from an area where we have the typical nanocolumnar growth of titanium dioxide to another area where we have compact nanostructure. Looking by confocal microscopy, we have this typical structure where we have some valleys here and we have hills and valleys with a difference in height of circa 100 nanometer for films which are 300 nanometer, 400 nanometer of average thickness. Not only that is what happened. If we look to the crystallographic structure, well, this is a TEM analysis of these domains, the hill domains and the valley domains. You can see here that the hill domains, they are formed by the typical nanocolumnar structure of the titanium dioxide, while the valley domains correspond to a very compact, extremely compact titanium dioxide situation. In both cases, we have the crystalline phases. We have a mixture actually of anatase and rutile, which is not to be expected because magnetron sputtering, as I said, produce the growth of amorphous titanium dioxide. Well, this is what we obtain. The question now is, what is the pattern mechanism? Why we obtain this pattern profile? Well, in principle, we have two hypotheses to deal with. The first hypothesis is a mechanical effect. So there is a certain transfer of energy or momentum of the lattice atom, which are moving, as you have seen, for a piezoelectric substrate, and they are transferring mechanical energy, momentum to the deposited atom. Actually, if you examine by laser vibrometry, these are experimental results, the surface of the piezoelectric film, the piezoelectric substrate with the film on top, you can see that there is this vibrating oscillation, as you can see here in this vibrating map, amplitude and phase map corresponding to the surface. That is a very strong dependence on frequency, that's clear, but you can see that changing the resonant frequency and moving along this map of resonant frequency of the device, we can induce oscillation which are considerably high, so in the order of 3-4 angstrom of movement of the atom. The surface is completely vibrating. So this is perhaps the most likely hypothesis. However, this hypothesis is somehow contradicted by some experiment that we carry out. For example, if we perform a similar experiment on this single crystal lithium niobate covered partially with a titanium, very thin titanium film, is a metal. So, and perform the experiment, we can see that in the uncovered area, the area which was not covered by titanium, we get the 2D pattern, while in the titanium covered area, we don't get any pattern. Moreover, if we carry out a comparative analysis of the nanostructure obtained by electron beam oblique angle deposition excited by acoustic wave affiliation, what we obtain is the typical nanocolumnar deposition structure, you can see here, but without any patterning. So it means that something else, in addition to the mechanical activation, should be in place in order to produce to the pattern. And the idea and the hypothesis that we are playing with is that in addition to mechanical properties, mechanical actuation, we have the possibility of electrical actuation. So actually, when we activate a piezoelectric substrate, these are simulations. We get the changes in the amplitudes, as we have already seen experimentally, but also we are producing a change in the electrical polarization, a difference in electrical polarization, which are illustrated in this map here at the bottom, where the difference in electrical potential between, for example, this area gray and this area in white is in the order of 10, 12, 14 volts, which means that locally the polarization degree of the surface is completely different in areas which differs in a distance for this frequency which we are using in the order of 0.51 millimeter. So with that, we have arrived to our hypothesis of what are the effects inducing this 2D patterning. And the idea is that in magnetron sputtering, what we have is a plasma that if we approach sufficiently close the substrate to the target, produce a plasma shift on the surface of the substrate, a substrate which is oscillating, and not only is oscillating, but also changing the polarity of the electric field in certain zones. While in other zones here, there is no change in the electrical polarization. So what we have assumed, and we are now modeling, is that in this area where we have a change in the electrical polarization, there is a concentration and acceleration of the ion beams of the plasma, which impinging on the surface are producing in this area a considerable compactation dB. As is happened in conventional technique using ion beams to produce the compactation of the deposition experiment. Very important for this experiment to keep the relation omega t smaller than 1, where omega is the frequency of the applied field and t is the ion transit time through the plasma sheet, which depends of all the plasma pressure and thermalization degrees on all the parameters that I have mentioned at the beginning of my talk. I have to say that the possibility of playing with acoustic wave provides also a way of tailoring the domain size. We are now working in changing the change of the domain, for example, by using other frequencies. If we use for the same device a frequency of 11.8 around this value, we obtain similar compactation in certain areas, but with a size domain which is much smaller than in the previous case. So the question is that you can move with the frequency from megahertz, some few megahertz to tenths of megahertz, and then change this patterning along the deposition process. With that, I would like to arrive to my conclusion very simply. I would like to vindicate the use of magnetron sputtering in an oblique angle deposition simply by saying that it is very critical to control the position conditions like plasma pressure, distant target substrate, and in energy of the impinging particles. If we don't control these parameters, we may have the results which are not in the line of the nanostructuration that is expected for oblique angle deposition. And on the other hand, if we use acoustic wave to activate the deposition process in an oblique angle deposition configuration, it is possible to pattern the deposition process and to get to the patterns which can be tailored, changing the position condition, type of acoustic wave. So there is within plenty of work and field to work with in order to have a patterning during the deposition process. Let me just acknowledge the support of some funding agency from the Spanish government and from the European Commission, which are the two main sources for this work. And finally, let me show you where we are. We are located in Spain, southwest of Spain, in a place which is called Sevilla. Sevilla is a very nice place with many very interesting historical monuments. Probably many of you know this monument, even if you haven't been here in Sevilla. This monument had been used for films, very famous films like Star Wars and classical films like Dr. Zhivago and many others. So, and with that, I would like just to finish and thank you for your attention. Thank you very much.
Thank you, Professor Lippi, for your interesting talk. Can we have a couple of questions? Yes, Professor. Professor Khan, you may please ask your question.
Hello.
Hello. Yes.
Actually, it was a nice talk. Out of curiosity, I just want to ask, as plasma is introduced in magnetron sputtering, is there any possibility of accumulation of charges on the nanostructure, or either the stoichiometry is disturbed in case of magnetron sputtering compared to thermal evaporation?
You mean that well, I haven't understood well your question. You say that well, in magnetron sputtering, indeed we have a plasma. We have charges, of course, in the plasma. The average electrical distribution in a plasma outside what it is called the Debye length is zero. So there is a compensation between negative and positive charge. But of course, if we apply an electrical field, we can move some of the charge out of the plasma. That is what happened in our oblique angle deposition experiment, where very likely there are argon ions which are impinging, they are attracted by the substrate. I do not know what is exactly your question. If perhaps you can.
I mean, actually, it's momentum transfer, na? In case of magnet transfer thing. So, any stoichiometry is disturbed, or it's fine as in thermal evaporation?
Well, I mean, in terms of chemical composition, so
Yeah.
if you are trying to get, for example, an oxide nanostructure, for example, titanium dioxide, you have to use typically a mixture of gases. You have to use, for example, argon and oxygen, very tiny amount of oxygen, in order to keep the stoichiometry of the field. Actually, what happens if you have a mixture of, let's say, for example, argon and oxygen, even if very small amount, the argon is the main sputtering ion, so argon ions will produce the sputtering, while the oxygen, you have oxygen going everywhere and also to the substrate. And although, for example, in the deposition of titanium dioxide, titanium atoms are arriving to the substrate, there are also oxygen molecules which are arriving to the substrate and produce the oxidation. So you have to compensate, or you have to add some oxygen ions, oxygen atom in order to produce the oxidation. But this has nothing to do with any energy or momentum transfer. It's just a chemical effect. I don't know if I have answered your question.
Okay, we have the next question from Professor Suzuki.
Okay, hello. Thank you. Nice talk. This is Suzuki from Kyoto University. So I have a question.
Hello, how are you?
About the 2D pattern on the piezoelectric. Are there any correlation between the wavelength and the pattern?
Yeah, of course. There is a strict correlation between wavelength and pattern. So in the first series of experiment, we have been using, we have exciting the piezoelectric substrate with 3.4 megahertz, and this the long wave is rather complicated. So it has not a very simple profile. So it have longitudinal and transversal components. So it's rather complicated. That's why we are planning to move to Rayleigh wave. But okay, let's stay with Lamb wave. And of course, the wavelength is in the order of half a millimeter, 1 millimeter in this area, while if we move to a higher excitation frequency, so the last experiment where we were using 11.8 megahertz, then the wavelength is smaller, and so it is the pattern size. So the pattern size is directly controlled by the wavelength of the acoustic wave.
But from the analogy of the fourth microbalance, the frequency or the wavelength can be changed during the deposition, I think. Is that right?
That's true. And that is a very critical point. So actually, what you have to do is a self. So you have to control the frequency. The frequency changing very little, but it's changing in the order of a few kilohertz during the deposition process. Because, for example, you have thermal effect. Also, it's not equivalent to have a piezoelectric plate free from anything on top that to have a piezoelectric plate with something on top of the surface. So the electric condition and the oscillating condition are changing. So And indeed, you have to have a self-feeding adjustment of the frequency, very tiny. Well, that is feasible, that is not complicated, but you need to self-adjust the frequency during the deposition, because as you say, like in a quartz crystal monitor, the frequency is changing with the amount of material. Here in this experiment, we are moving within thin field, so we are moving with thicknesses in the order of a few hundred of nanometer, but still the frequency is changing during the deposition. And you have to readjust to have a kind of feedback system to be readjusting the frequency. That's true.
I see. Thank you very much.
Welcome.
Do we have any other question? If none, then let me thank Professor Leopold once more. Thank you, sir. It was a very interesting talk.
Okay.
With this, we move to the next speaker. Dr. Shashank, can you please share the screen?
Yes, I'm sharing this.
So the next speaker that we have is Professor Levent Trabzon. He is a faculty member of mechanical engineering at Istanbul Technical University, ITU. He completed his MSc degree from Carnegie Mellon University, Pittsburgh, and PhD degree from Engineering Science Department, Pennsylvania University, State College in year 2000. He was the founder director of Nanotechnology Research and Application Center, and he's currently director of MEMS Research Center. He has published more than 90 research articles in journals and conferences with 7 patents. One of his awards was the Technology Award from Elginkan Foundation for his contribution on MEMS technology. His research interests are primarily on MEMS design and fabrication, nanotechnology materials, microfluidics, surface science, and polymer nanocomposites. Over to you, Professor Levin.
Okay, thank you very much for introduction. And share.
Yes, please.
Yeah, I'm doing that now. Share. This happens. Do you see my screen?
Something is coming up.
Yes.
Yeah.
You see that?
Yes, it is there now.
Good. Okay, good morning from Istanbul. It's almost 9 a.m. at the moment, but and I am also honored to be invited to this conference, very prestigious conference. I'm going to give a short talk on what I understand, what we have done on the GLAD thin film techniques and applications. Specifically, I'm going to present some findings from our research regarding silicon nanocolumns, and specifically application of those nanocolumns on engineering to 3 different engineering applications. But before going into details, short overview is the following. First, I would like to give some brief introduction in GLAD method. Each one of contributors already did, but it's better to refresh or present my understanding. Also, I'm going to express some how we grow the silicon nanocolumns applications in biology, and using the same or similar columns and study modeling and experimental studies on hydrophilicity on silicon nanocolumn surfaces. And we also I'm just also give a little bit about the silicon GLAD films in solar energy harvesting. And 2 more examples other than silica, actually, silicon, silver, and then nitinol GLAD films. And then I conclude my talk with a short conclusion. We have already known that GLAD method, glass angle deposition, has been studied so widely in the last 3 decades actually. The basic mechanism behind that shadowing effect, and then you are able to sculpture the thin film morphology by playing with the deposition, the parameters, and also it's at the end, you're gonna obtain a porous medium. There are basically 2 main approaches. First, you're using a point source. In the point source, it means that thermal evaporation or E-beam evaporation. In our case, we solely concentrating on the E-beam evaporation. So we have utilized point source approach. But on the other hand, just we have seen very nice talk in the previous talk given by Dr. Gonzalez. The surface source has been also utilized. But the mechanism and dynamic environment is very much different than the point source, so that you should be very careful about in using the surface source, specifically using by means of the sputtering GLAD film depositions. And if you cleverly use the parameters of the deposition techniques, you can come up with the very different, very nice, the geometries in 3-dimensional as well as in 2-dimensional. And in a simplistic way, I can say that if it just to replace that GLAD film morphology in a thin film, the morphological models, it's gonna be columnar zone T structure, but without ion bombardment. That will be by using oblique angle deposition and some other the surface properties, you can come up with the columnar width less than smaller than 100 nanometer, and porosity up to 80 percentage, so that the main mechanism behind, as already mentioned, that low atom mobility and the atomic self-shadowing on the surface. This is the GLAD system in our lab. This is almost homemade system, but as you see, we have the E-beam evaporation over here, and we have the the sample put over on the wafer or whatever you call. Then you're gonna get the thin film graft, GLAD thin film graft on the surface. And fortunately, we have recently purchased another system, and in that there is a GLAD deposition apparatus in the vacuum system. The details of the morphological features of the GLAD films, it is the porosity or the geometry of the columns changing from a couple of nanometers to the 100 nanometers or even above, so that would be even in the cross sectional wise, you're gonna have very nice porosity or geometrical formation in GLAD films. That would be very much similar to the biological surfaces it can be seen in our bodies. Like, for example, one of the diagram on the right-hand side, as you see, that is the scanning electron microscopy of corneal epithelial basement membrane of macaque monkey. So that the membrane structure is there are some porosities in the micron side. There are some porosities or topography surface gonna be very much similar to the topography you can obtain by using GLAD film. So that we realize that we can grow nano surface, nano dimensional surface by GLAD, similar to the membrane structure that on which you can grow cells, epithelial cells, and we have done it. We have grown such films based on the silicon. As we have already discussed, in details in the previous talks, you can easily make helicoidal growth by silicon by changing the turning speed, RPM value of the substrate, or changing the deposition rate. So the columnar width in our case in the range of 70 nanometer and spiral width in the range of 150 nanometer. In our case, the film thickness is around 1 micrometer, and as you see on the right-hand side, the porosity can be easily modified by film growth parameters. And also, you can even play with the, how you are manipulate the substrate. You can get the integrated growth. In this case, this is a silicon material. Again, the incident coming vapor angle is around 80 centigrade degrees here, and you can get zigzag structure. You can get helicoidal structure with different properties, so that this is nothing but the just engineering of the nanostructure in nanoscale. So, moreover, you can engineer the cross-sectional cross-section of the columnar films by using this in this following method. Instead of using the constant RPM in turning speed, you can section-wise changing the RPM value of the turning speed of the substrate. As you see over here, if the RPM is equal to in the A section equal to the B section, you can get very nice, circular cross-sectional nano columns. But if you're going to change that, like if the RPM A is much faster, if the substrate is turning much faster than in the section of the B, you can get elongated growth in the region of the B's, so that you can get very nicely square-like structures that will modify, by using that, you can modify the surface energy of the films. That makes very much difference in applications. Like, for example, actually on the right-hand side, these are nothing but these are some dirts actually. These are, but since you have the very much enhanced shadowing effect, and by using the changing the RPM at certain locations by means of the enhanced with shadowing, you can get a square-like, very much bigger, the columns. Or if you're gonna modify that in a triangular mode, you can get a triangular shape of the shadowing. But these are on the left-hand side. Those are happened because of the dirts on the surface. On the right-hand side, that is the square-like columns, columnar forest, and at the bottom, these are the triangulated columnar growth on the surface out of silicon. Okay. So what we have done as an experimental setup, we have grown different silicon columnar structures having a different level of symmetry. As in the case of on the top of them, we get a elongated to a certain direction. We call that 2S level of symmetry line. 2S level of symmetry line. Just it's a line kind of symmetry you have. If you're gonna arrange that changing of the turning speed of the substrate accordingly in three different sections, you're gonna get level of symmetry triangular. We call that 3S. Or if you're gonna get the square-like cross-sectional, as you see over here, cross-sectional columnar structure, we call that 4S structure. So what we have done we have grown, let's see, yes, we have grown mesenchymal stem cells on such silicon surfaces. And on the left hand side, as you see, these are the observation of the cell morphology after 7 days of culture in direct contact on silicon surfaces. But in all cases, we haven't utilized any growth factors. There is nothing to enhancing or moderating the growth, the fascia in those, in those culturing. And as you see from A to F, there are a very much different behavior of the mesenchymal stem cells on different nanotopographies. So that will be also seen non-radioactivity cell proliferation, experiments on the right-hand side, and you can see clearly over here. That one is the yellow one is the bare silicon, no nanostructures. In some nanostructures, as you see, actually there is no much difference, even less proliferation. I mean the cell activity. But in some cases, as you see over here in the forest means that square-like cross-sectional GLAD films. That would be very much similar to the almost TCP value. TCP value is the tissue culture polystyrene. That is the culture you can get the best result, because you have all sorts of ingredients so that cells can be grown in a much easier environment. But without putting any ingredients or any external, the food, whatever you call, without any one of them, you can get almost similar results in the 4S case. Actually, what we have noticed that the mesenchymal stem cells only on the surface with 4S symmetry, silicon GLAD films, we can get calcium, phosphor deposition on the film, so that we can get on the 4S case by measured by the SEM, the elemental analysis, but not the other ones, so that the mesenchymal stem cells somehow on the 4S surface, they change their properties into the osteogenic, the structure or property, so that they're gonna deposit calcium and phosphor. And if you look at the ratio, the calcium and phosphor is almost 5. That is almost the same ratio what the osteogenic cells doing in our bodies. We also put some more effort to understand what's going on, because hydrophilicity is gonna be enhancement factor in such cell proliferation. Okay, so that we have studied that and model, try to understand what's going on based on the geometry. We have measured on 3 different films, 2S, 4S and the 3S and the 4S silicon films by using the AFM measurement in details, and we come up with the columnar diameter distance between columns in different films, and minimum, maximum, kind of hard work to understand how the geometry is changed, or what will be the characteristic of the geometrical features on the surface. By using such data, those data, then we are going to model the hydrophobic or hydrophilic behavior, depending on what kind of models or approach. Actually, as it is well known that there are 2 well-known models. One of them Wenzel, the other one Cassier-Baxter model. But to understand, which model fits well to our experimental results, in the experimental measurements, we measure contact angles on the surface. You see, for 4N, we got 10 degrees, 3 and 15, and 2 and 27 degrees. And we also calculated based on the Cassier-Baxter and the Wenzel model to compare that the experimental result. But unfortunately, Wenzel cannot be applicable to this, because of the roughness is bigger than 1. And so that we concentrate on the Cassier-Baxter model. In the Cassier-Baxter model, the drop size, small x corresponding to drop size, while you drop to the original drop size, you are dropping from the instrument. And the big X is the size of the drop when it's gonna be interact with the surface. Anyway, the roughness is calculated by this, the model given by the literature. L is the lattice constant, and B and H are the radius and height of the pillars, respectively. And the solid fraction is also calculated, B times B squared divided by L squared. L is calculated kind of by using the periodical lattice approach, like the thickness of the column and the 2D. I mean, the distance in between, and the plus 2D, the thickness of the columns, and B is the D over 2. Based on those numbers, we end up with the calculation of the roughness and the solid fraction in each case, so that at the end, what we have got is the following. As I mentioned just in the previous slide, but let me repeat one more time. X is a defined nucleus size, while you drop the the original drop size. Big X is the drop bottom radius when it is interact with the surface. In Cassier-Baxter model, what we have seen that when the X, small x, is bigger than big X, the model is going to be in good agreement with our experimental results. So that even though it's not perfectly matched, but the trend and the level of numbers is going to be well matched. That's why we come up with the the structures we have developed, giving us a sunny side-up state. Actually, such a the finding is very well matched with the biological findings and much more biological activity or osteogenic change of the mesenchymal stem cell we have seen in the previous slides. It is well agreed with the previous results. We also studied penetration, as I'm not mentioning too much, but it's going to be changed by the roughness. Again, that will also be utilized, that Cassier-Baxter, but in the case of small x bigger than big X case. A couple of years ago, in one of my Master of Science students tried to develop silicon GLAD films in solar energy harvesting, solar cells. Actually, what we are trying to do, we are trying to do porous silicon films and embedded in the PDAC, PSS, the polymer, so that we are trying to harvest electrons from the solar energy. Anyway, these are some of the the pictures we have got it, and we also characterize that material properties like surface hydrophilicity increase with increasing porosity in that case, as you see on the the surface. That is also related to the previous results. And we also measure the reflectance on the surfaces. A flat surface is represented by the blue line, and the changing the characteristic of the more porous surface exhibits less reflectance, as it is expected. It's a good for solar harvesting applications.
Professor
Moreover, we also measured that transmittance measurements on
Professor
pilot,
Levin.
PSS. Yes.
We are almost at the end of the talk as per the timing. So would request you to.
Just a couple of more slides, I'm going to be done.
Okay.
Okay, just give me a couple more. Transmissions is going to be not bad respect to the glass. Anyway, I'm just giving two more slides. We also studied, it's unpublished data, but the GLAD, silver by GLAD is not easy material, as you already know that, because the melting temperature is not so high. But you can notice that higher deposition rate induces pseudo lower surface mobility. This is one observation we have seen. And also we studied nitinol GLAD films. This is some examples. Also measured that XRD data on the nitinol GLAD films. When you deposit nitinol GLAD films, it's going to be non-crystalline. But after you thermal anneal that under vacuum, you get very nice crystalline nitinol films. As a conclusion, I would like to thank you again for conference organizers to invite me to this very nice conference. And also, I would like to say, as my last word, we are open to collaborate on GLAD research, and you are very welcome. And if you like to, like to do some collaboration, please don't hesitate to contact with me. Thank you very much.
Thank you, Professor. Do we have some questions? Yes, Dr. Mukesh.
It's a very informative talk. I have only very small question about your silicon and PSS solar cell. So have you observed any efficiency for the device?
Unfortunately, we haven't measured yet. This is an ongoing, study. Fortunately, in the coming months, we come up with very nice, results.
Okay, thank you.
No problem.
Yes, Professor Singh.
Yeah, it was a nice talk, Professor Levin. So, yeah, it's like I have one query, like because you have shown your contact angle measurements over different symmetry of the samples, like one which having square, triangular, or rod shape. So I have like one query, like have you measured the effect of symmetry of these structures on the shape of the droplet, which you put on that? Is there any anisotropy?
It's a good question, but as I understand correctly, you're asking me the effect of the droplet shape on the contact angle, right?
Yeah, it's like is your droplet was symmetric when you put on the triangular symmetry, or do you observe some kind of anisotropy? Like,
actually, we haven't studied through this direction. I mean, we haven't studied that the shape of the droplet affect on the surface. It's a good question, but I will take it as an advice.
Okay, thank you.
No problem.
Any other question? Okay, so let's thank Professor Levin for the interesting talk. Thank you.
Thank you very much. Bye-bye.
Bye-bye. So now we come to the next talk, and in fact, the last talk of the session. And I'm very happy to invite Professor J.P. Singh, who also happens to be my PhD supervisor, for his talk. Professor Singh has obtained his PhD from Inter-University Accelerator Center, India, and is currently working as professor at Physics Department, IIT Delhi. He did his postdoc from RPI, New York, and his research involves study and applications of GLAD fabricated nanostructures, SIRS, nanomechanics, CO2 conversion, nanogenerators, graphene-based sensors and actuators, wetting properties of thin films, oil-water separation, clean air, and many more. Professor Singh has received several awards, such as Fellow Medal from International Association of Advanced Materials, Sweden, Outstanding Faculty Award from IIT Delhi, and others. He has published more than 110 research articles, 10 book chapters, and holds 2 patents. Professor Singh is research advisor of several international academies. Over to you, Professor Singh.
Yeah. Hi. Just trying to share, but yeah, now I can share. Yeah. Can you see my slide maybe?
Something is coming up. Yes, it is there.
Yeah, it is there. Okay. Okay, let me just. Okay. So thanks, Rupali. And I just I'm obliged to see many people who are working in GLAD and almost all the researchers for GLAD community to be here. And today I'm going to discuss with you, show you some of our results which we obtained from glancing angle deposited materials, and which are really having their applications towards like biosensing or maybe kind of a like some kind of actuators which are used in medical science. So these rods, which like these structures which we grow. So I'm not going to discuss anything about like what is glancing angle deposition, because our previous respective speakers, like from yesterday and today also, they have talked in detail what is glancing angle deposition technique. And so that was also given by Professor Zhao and Pierre. So you know that. So so we are also having a glancing angle deposition system in our lab. We have 3 systems, e-beam deposition based as well as the thermal, and we also have low temperature deposition system which can go up to liquid nitrogen temperature. So in this talk I will focus only on the nano rods, silver nanorods, which were grown by glancing angle deposition. So these structures which were we used here are either they are nano rods or they are kind of a zigzag kind of structures. So now the one thing about the silver nanorods is that actually they oxidized very fast in the air. So just to avoid that, so what we do actually, we package those nanorods, our nanorod substrates, under clean room, which is class 1000, sorry, to avoid the oxidation and contamination. And then we found actually it can be used for after several months. If you open, they are good to go actually. So just for let me just take this here. Yeah. So just here I'm just showing you some of the research area which we are working here at IIT Delhi. So these structures which we grow by glancing angle deposition. So like one of the area which we are working is basically the nanomechanical properties. So we grow a lot of like composite material which we using these GLAD structures and measure their mechanical properties, and also the proper mechanical properties of individual nano springs and nano slanted nanowire. As well as recently we worked out basically the anisotropy in the frictional measurements, like if you move across the slanted nanowire, or if you have a two nanorods like zigzag kind of structures, then we found actually the coefficient of friction is has anisotropy in different directions. So another area which we also worked for basically regarding this oil water separation, that was one application which we got also patent. So there we shown actually if we use these nanostructures, and we can one can basically use basically just by using the oxidizing or reducing gases like hydrogen and oxygen, we can control the contact angle almost like from 0 degree to like I think something like 160 degree, 167 or something, yeah, around that. So we can control the wetting properties of these nanostructures. Also, one of the and the application wise, we have shown that these kind of structures can be used for oil water separation. One of my previous PhD, she has done a lot of work on this area. And another area which is we are also very active is basically the study of oxygen vacancies in metal oxides. And for that, actually, we are studying basically the different, we try to fabricate different photocatalysts, and those photocatalysts, some of them actually we are using for kind of CO2 adsorption, those kind of mechanisms. Also their optical properties, how they get affected by introducing the controlled amount of oxygen vacancies inside that. That kind of study also is going on in my research group. And then for bio-related things, what we have done actually, like yesterday you heard with one of my students, like he has talked about, like we use these silver nanowires, and we made some kind of colorimetric sensor. So just by changing the silver nanowire, which changes the color, we can one can get the idea about basically the bacteria, if it is live or dead. We also worked on, we are working on, not worked on, we are still working on, our research interest is basically detection of different biopathogens like bacteria or virus based on their signatures, like the Raman signatures, surface enhanced Raman spectroscopy. So this is one area we are working, and currently this very recent work we have done, we just fabricated one ECG electrode, which is electrocardiogram electrode, which by using these silver nanowires. So today's talk, I will just briefly, I will just discuss about a little bit about the search applications and the ECG electrode. Let me go, and then so if you just see about this the bacterial detection using this silver nanowire. So the gist is that like most of these biopathogens, like bacteria, if you talk about the living cells, they their metabolic system is such that they emit they evolve hydrogen sulfide gas, and by just detecting the small amount of the hydrogen sulfide gas from these pathogens, one can detect basically if these structures are alive or they are dead. So that was a very simple measurements, and so this was done like using the colorimetric measurements, just by detecting basically the color of the substrate, as well as basically we found, because the material get changed from silver metal to silver sulfide, so their surface chemistry has changed, so their wetting properties were also changed. So just by getting basically the idea about their color change as well as their wetting property change, we could able to detect the small amount of even the smaller amount of like hydrogen sulfide gas, which is coming out from this bacteria. And then finally we could able to see that even we can detect, basically you can see here that we can detect basically because if the bacteria is dead, then there is no almost very small amount of H2S detection is there, and so that color, from the change in the color, we can figure out also from the contact angle, which is a huge change you can see here. Also we have also find out like on E. coli, and this result I'm showing for E. coli, but we have done from 10 different kind of bacteria, and gram-negative bacteria we found this is quite effective. And there we found actually for even for antibiotic resistant bacteria also, because if bacteria is antibiotic resistant, you can see if this idea works out, and we could able to differentiate between the antibiotic resistant bacteria or the normal bacteria. And so now, this since the work was already shown yesterday, so I'm just not going in detail there. So now I'll just discuss with you our very recent work which just came out. So here, what we have done actually, we collaborated with the National AIDS Research Institute in Pune, and so the idea was we have used our this silver nanowire arrays, and then this HIV one which we have used, which was actually taken from the patients. So these were all are actually clinical samples, and this about the HIV is like you can see the HIV virus is kind of envelope virus, and it got like 2 strains of RNA, and this virus has some kind of like you can see these structures, outer structures are there, which are glycoprotein, and so this virus get actually attached to the cell through the receptors, and so overall this virus we have the so there are envelope proteins as well as genetic materials. So when so the idea was actually if we actually can we find out basically the your like surface enhanced Raman spectra of these kind of structures, and for that actually we have taken 5 different subtypes of HIV virus, and then we just idea was just to put onto the substrates, and also we sometimes we also have like diluted with different kind of solutions. I will just discuss later on, and then find out basically their search spectra. So this was the kind of methodology what we obtained. We obtained the samples, then 5 different subtypes were, and we have also just kind of like compare with the gold standard, which is the PCR, and different kind of solvents is used. I think we have written only 2, but there are others also. So different solvents, different types of types, and then we have also worked with like we have also spiked the virus also in the plasma, and then so then these results were obtained. So you can see here. So so these results are actually on clinical samples. So we can see that the spectra of like these 5 subtypes which were shown here, it was so overall if you just see the search spectra is not that much kind of a different for kind of like all these subtypes. So but yeah, it's like we could able to figure out the search spectra of the HIV. But one of the very interesting thing which we found that was very interesting, that it could able to our data could able to differentiate between the different tropic of HIV, like because HIV we know is having a it shows the tropism, like depending on the because depending on different cells there are different types of strain like which HIV can HIV is having actually. So like X4 is one tropic of HIV, R5 is another tropic. So so you can see that these 2 spectra actually are we are lucky enough to get we could able to differentiate by their some differences in their spectra. Otherwise, most of the time you'll find like in most of the these bio or organic materials, biomaterials, actually their spectra are quite alike, and you have to do some kind of statistical analysis to figure it out basically the differences. So then we have also figured out like in one of the strain like which are from the Uganda, like you can see that these envelope proteins they belong the peaks which are we associated different peaks which are associated with these envelope proteins, and we compare it with basically in with the controlled sample which is the plasma control. And we have done for all the subtypes. Due to the time, I'm not showing in detail basically all the results here. But then finally, I just told you like because the problem is like we need some kind of statistical analysis method because the differences are in the spectra is not that much. But yeah, we were lucky to see the difference in the tropism actually. That was good actually because there were some clearly some different peaks, because these binding units, if you see, we just discussed, this GP120 protein, which has a difference depending on the different tropism. So that was able to clearly resolve in the peak. So that was a good part. And then in the we have run this simulation, which is not the simulation. This statistical method. We have used the statistical method, which is principal component analysis, and we could able to differentiate between the HIV positive and negative, as well as you can see here in this C part where this kind of like the strain, which is X4 strain tropism, is clearly differentiated by the R5 another strain. So that was something good part actually. Now I will show you one of our recent work which we have recently done actually for basically fabrication of ECG electrodes. So ECG is kind of an electrocardiogram, and we know that it just like heart actually starts some kind of it just records the electrical activity of basically the heart, and then heart actually gives the electrical signals which moves throughout our body, and they have some kind of rhythm, and according to that we know that the blood actually flows. And so I'm not going in that much detail, but based on the basically these electrical signals in the heart, in the cardiac muscles, there are some polarization of heart, depolarization or polarization of the heart, and which actually generates some kind of a wave, which is like which is shown here in this graph. And for physics point of view, it is just for us, it is just for the a kind of a voltage versus time curve. So these P, Q, R, S, T. So P is basically polarization of basically the atria, and QRS complex are basically the ventricles, and then again the repolarization of basically the heart, cardiac muscles. So this actually goes on, and then in any ECG kind of like graph, you will see these signals. So what happens actually? So this for doctors, this is very important because based on the kind of the shape of these curves, their position, as well as basically their kind of size, doctors can actually determine the abnormalities in the heart. So so the problem currently what is used actually currently people use. So there are two systems. One is basically the system which is used in the hospitals. They use kind of like very kind of bulky kind of system, which where you have a lot of like wires, and there might be tensions. So it actually measures the electrical kind of these electrodes are measuring the electrical impedance, so or electrical signals from the skin. So so because of that, there are some kind of a skin preparation is also needed in most of the case, and we use some kind of electrolyte gel. So these electrolyte gels are used, and they use silver chloride kind of electrode, which is placed on the body. And the problem with that, actually, for a long time, you see there kind of a risk of infection. There's you need a skin preparation. Also, if body moves, then that also creates some kind of a noise, which is known as wandering noise there actually, and that causes a problem in the ECG signal. And also for long-term heart monitoring, it is not possible to use this kind of system, which is bulky also. And the impedance is and one of the biggest problem with this gel is like for a long time use, this gel actually solidifies, and its impedance also increases a lot. So there are like a couple of problems with the current ECG electrode and system. So what we have done actually, we have fabricated these using this glass angle deposition, the silver nanorods, which I have shown the image before, and then we embedded these structures under under PDMS, and so that actually partly some of the part is actually outside. This is not shown here, but actually some of the nanowires are outside, and then these structures, which is kind of these nanorods which are coming out, and this you can see here the actual so I'll show you the actual electrode also. So these structures are used as the ECG electrodes. And so now the point is like, what is the advantage of these silver nanorods embedded PDMS ECG electrodes over the conventional electrodes? So one of the things is that these electrodes which we fabricate are flexible, stretchable, and we have also measured basically the mechanical properties. They are mechanically robust because these nanostructures which got inside in the matrix of PDMS get fixed there. And also so they you can reuse it actually. We have done also peel test also, so you can reuse it, and so they fit for long-term heart monitoring kind of thing, which was not actually currently available for conventional electrodes. Other than that, actually, we have also found, because of the increase in the contact area, because they are actually so the specific resistance also, overall the impedance of this skin electrode impedance in case of our electrode is much lower compared to the conventional, which is one of the biggest advantage. And moreover, this material is also biocompatible, and we also found like continuous use, it is not producing any kind of irritant effect or no dermalia. So that is, and moreover, this is dry. So just by controlling basically the PDMS and curing agent amount, we have made the top layer like kind of a little sticky. So it doesn't need any kind of glue or something. It sticks by itself actually. So so these all kind of like novelty and feasibility I have just talked about. So we can just skip this slide, and I can show you basically. So these were the electrodes which were fabricated recently in our lab. So which is kind of compatible with the all the machines, ECG machines also, which is available in the market now. But the best part is actually we have also basically make some kind of a wireless some kind, yeah, here. So the best part is basically here I'm just comparing the these electrodes with the conventional electrodes. So you see, this is our skin, the outer side of the skin, which is stratum corneum, and then epidermis, outer epidermis. So when you use the gel, the problem is that this gel actually get like solidifies over the time, and the impedance changes, and then basically the electrode and skin impedance increases, and then we won't able to get the signal, because signal is very small. It is of the order of few millivolt. So it get because of high impedance, it get dropped there. So we need a very low impedance here. So that's why in industry they use electrolyte gel, conducting electrolyte gel here. In our case, where we use silver nanorods, and another problem is if it moves little bit, this area, contact area moves, then you will have problems in the noise, electrical noise signals, which you can you will get in the basically in the circuitry there. In our case, because they are the nanowires which are coming out, so we can just we can push fit inside the skin, so they can little bit peer inside the skin, and then they can go move inside the skin. They get fixed there actually. So that actually, and also large specific area also reduces the electrode and the your electrode as well as the skin impedance. So that was thing. So here we have just compared that. So you can just see here it's a great difference. This blue one is our curve, our electrode, dry electrode. Without using any kind of conducting electrolyte, we could able to achieve the impedances which is much lower compared to the basically the commercial one. Now we have also made some kind of a unit, small kind of a setup, so that actually this electrode, which so we can avoid basically the display part. So the electrode signal this is made in-house. So the whole kind of circuitry is made there, in the lab. So actually these signals actually we can process in small circuitry, and then it can transmit to the mobile phone. So we can use the cell phone as our display and basically the analysis kind of analysis unit there. So here I'm just showing you basically the comparing the signals which we obtained from one of the typical signals which we have which were obtained basically, this is a raw data which we obtained by without any image processing, which is obtained from our electrode using this circuitry, and which is from noise point of view, other thing which we found is even much better than the conventional, which is commercial electrode. And then we also made some kind of Android app which is there, which in the mobile phone, which can get the direct data by using the Bluetooth transmitter and from the ECG electrode to the mobile phone, and then it can actually process all the signals, and we can have 12 leads at least simultaneously also. So that is one of the work which we did recently. So so because I just saw actually that it was like going to be 12, so that's why I just immediately I shortened my talk. So I think that's it maybe. Yeah. Thank you. And this is my team here. So we are so this work was mainly by Sarjana and Yogita, two students who are working in this area. And I am like thankful to all the funding agencies. Yeah. Thank you very much for your attention.
Thank you, Professor Singh, for a very interesting talk. I think we're going from lab on a chip to ECG on mobile, and everybody will be having it. Great. So can we have a couple of questions? Any questions for Professor Singh? Okay, then I'll ask you one question. Have you thought about commercialization, and what would be a typical cost of having such a sensor?
Yes, like we are actually getting in touch with we are already in we have patented this, and then we are already in touch with one company in Bangalore, and also with AIMS Rishikesh, so that there are a couple of doctors which are involved actually. So yeah, we are already in process. So yes.
Great. Okay, so if there are no other questions, let me thank Professor Singh once again on behalf of everyone. Thank you, sir. And I would now like to hand over the session to Dr. Shashank.
Okay, so thank you very much, Dr. Rupali, for chairing the session. And I want to thank every speaker for their excellent talks and participants for attending it very patiently and carefully. So now we have a break for almost 2 hours. So we will be meeting again at 2 p.m. sharp, Indian Standard Time. And all are requested to be online with your camera on for a group photograph at sharp 5:15 p.m. IST. So please make sure you will be there for a group photo. So thank you very much, everyone. So we can meet again at 2 p.m. Thank you.
The Nanoscale Research Facility is an extensively equipped central facility at the Indian Institute of Technology, Delhi, for research and innovation in the area of nanotechnology, which holds enormous promise for the future. The nanotechnology deals with synthesis and fabrication of materials in the nanoscale, that is, in the range of 1 to 100 nanometer, a nanometer being a billionth of a meter. When materials are synthesized in the scale of a few nanometers, their physical, chemical, mechanical, and other properties change dramatically. This opens up enormous scope for studies in control over properties of various materials for a wide variety of applications. The nanotechnology has already started creating the impact on our lives with a vast range of applications such as nanomedicine, nanoelectronics, memory devices, energy harvesting, biomaterials, consumer products, etc. Future applications for the nanotechnology seem to be limited only by the creativity of researchers. Realizing the need for new technologies and solutions for the society and the country, IIT Delhi has been laying great emphasis on research and innovation.
IIT Delhi has created close to 100 crore facilities on its campus, and we are further augmenting some of these facilities. Many of these facilities are available for researchers from all over the country.
The Nanoscale Research Facility was established in August 2010 with the support from Ministry of Electronics and Information Technology, MITI, and IIT Delhi. The facility consists of Class 100 and Class 1000 clean rooms with several state-of-the-art fabrication, thin film deposition equipment, and characterization facilities. The research program of NRF has been focused on both thematic areas of national importance and basic research with importance to the development of nanoscience and nanotechnology. Faculty members from different departments and centers of IIT Delhi are contributing in cutting-edge nano research at Nanoscale Research Facility. The various facilities available at the NRF fall broadly under two labs, namely the Characterization Lab and the Fabrication Lab. The Characterization Lab at the NRF has a wide range of sophisticated instruments to enable structural, morphological, surface, electrical, and magnetic characterization of materials. The Fabrication Lab of the NRF is equipped with several advanced and sophisticated techniques to make nanoscale-sized patterns designs to deposit the thin film dielectric, semiconducting oxides, or other materials as well as a range of materials. The lab has an E-beam evaporator, a sputter deposition system, and a thermal evaporation. Some other equipment here: an E-beam lithography system, a maskless lithography system, a mask aligner machine, and a wire bonder.
We have several world-class facilities for fabrication and characterization of nanoscale devices. These facilities are open to all academic institutes and industries. There is an online booking system is in place for booking these facilities.
As a result of relentless research work going on at the NRF, a number of achievements have been made in processes, materials, and devices developed and patents obtained. For example, the researchers at the NRF have developed nanostructure and process for removal of organic dyes from polluted water, fabricated microfuel cell, fabricated 2D photonic crystal for OLED, developed method to enhance SERS signal of bacteria using nanorods, fabricated nanowire photodetector, and developed nanomaterials for removal of heavy metals from polluted water. The research program at NRF has been focused on areas of nanomagnetics, nanophotonics, nano photovoltaics, nano electronics, nanomechanics, and biosensor-based devices for health, agriculture, safety, energy, and environmental sectors. Going forward, it is proposed to develop working prototype of nanoscale devices such as explosive detection device, ultra-sensitive magnetic field sensor, soil analysis system, microfuel cell, detection setup for marker of prostate cancer and malaria. In addition to developing and fabrication of working prototypes, it is also proposed to explore new approaches for developing several nanoscale devices.
Using the facilities of NRF, several deliverables related with nanophotonics, nanomagnetics, nanophotovoltaics, nanoelectronics, and biosensing have been successfully demonstrated. The present NNETRA project